at an affordable cost which is sustainable. As a part of this effort, SWCC joined with the IDA to organize this conference with the specific themes where we are able to bring innovative minds around the world. And I hope this conference will bring some of the brilliant ideas which shall to be a game changer in desalination industry that enable us to produce healthy drinking waters for everyone, everywhere at affordable cost, which is our dream. Moreover, by organizing this conference, we are able to gather the specialists, scientists who are heavily engaged in the field of desalination and which has given opportunity to share the knowledge and exchange information in this area. Yesterday, actually, we have wonderful pre-conference workshop in brine mining. And today, during the 3 days, we are going to cover 5 themes. The first theme will be about innovation in desalination facility, design and operation. This will be this morning. And in the afternoon, we'll cover the green desalination technology and brining management. For the second day, we will cover 2 themes. The first theme in the morning will be about innovation, about innovation in desalination facility, design and operation, and followed by the green desalination technology and brine management. The last theme will be about the road mapping of desalination innovation. And also we are going to arrange a tour to Shuaibah desalination plant with a magnesium enrichment facility on Wednesday afternoon. In addition to that, we'll arrange also a visit to Rabigh 3 desalination plant on Thursday, June 2nd of June. Before ending, I would like to thank IDA President Carlos Cousin and Secretary General Mrs. Shannon McCarthy for providing full support to this conference. A special thanks due to His Excellency Abdullah Abdul Karim and also His Excellency Abdurrahman Al-Fadli, the Minister of MIWA, for patronizing this conference. Additionally, I would like to thank all the participants who are making this conference or who are attending this conference, as well as speakers and attendees. It would not have been possible to make this conference happen without the effort of organizing team led by Manal and also the DITRI team. I am really appreciate their efforts, and many thanks are due to them. Finally, I am strongly believe that the outcome of this conference is not only tangible, but will be something amazing that will be a game changer for the desalination industry. I hope you will find this conference enjoyable to all of us, and thank you.
Thank you so much for your words of welcome, Dr. Ahmed. I think we can all agree that this will be an amazing conference just by looking at the agenda. Thank you. Now I am delighted to welcome the IDA's Secretary General to the stage, Ms. Shannon McCarthy. Ms. Secretary General, please join us on stage. Thank you.
Assalamu alaikum. Good morning, Your Excellency Governor Al Abdul Karim, Your Excellencies President of IDA, Mr. Cousin, Director General of DTRI, Mr. Ahmed Alamoudi, ladies and gentlemen. It's my sincere pleasure to welcome all of you to the Innovation-Driven Desalination Conference organized in partnership with IDA, SWIC, and DTRI. I'd like to thank our team members for all their intricate coordination efforts, incredible support in assembling us all under one roof again, and for the gracious hospitality in such a beautiful country. A special call out to our team members who have worked over the last 2 years to collaborate and bring us all together with a dynamic technical program. First, I'd like to recognize Ms. Manal Alamadi, Salam Al-Katani, Muhammad Al-Shai, Alessandra Michelangeli, and Jennifer Landini. In addition, and most importantly, I would like to thank our sponsors whose support has helped us to enrich the program we will share with you over these next 3 days. Our mission today remains critical. Global warming is a water crisis. We have seen increased droughts around the world that have turned formerly lush landscapes into deserts. Increasing populations and industrial use of water all over the world are putting intense pressure on existing water supplies. And heretofore, dependable freshwater sources are simply no longer reliable for hundreds of millions of people on our planet. As we know, this also affects food security. The goal of IDA, a nonprofit, United Nations recognized organization, has never wavered. For the last 49 years, it has always been and will continue to be our responsibility to encourage essential research and development into innovative desalination solutions that will ultimately benefit both the people of the planet, people and our planet. We have done so and we will continue to do so. In this way, the IDA community, which the majority of the people in the room are part of, represents the very best minds in solving the looming water crisis. Over the next 3 days, you will hear about some disruptive technologies from our distinguished speakers that could very well ensure a regenerative water economy. We are very excited about the knowledge that will be shared and the exchange of ideas that will result from our discussions. I fully expect that the pending discourse will help us find ways to minimize the cost associated with desalination, and that prospect alone makes this a dynamic time to be working in the industry. It has been our pleasure to jointly organize this conference with the technical team of DTRI and SWIC, with leadership from our colleagues Dr. Ahmed Alamoudi and Engineer Nikolai Vuchkov of DTRI, and our IDA Technical Program Committee led by Mr. Borja Blanco. His Excellency, Governor Al Abdul Karim, has personally worked with us on expanding the conference program to provide opportunities for additional workshop discussions on key subjects like the role of innovation to protect the environment, harvesting resources from desalination brine, and essentially creating zero-cost water production, on science and laboratory principles to support innovative research, on artificial intelligence for early warning systems of harmful algae blooms and jellyfish attacks on desalination plants, and energy and carbon reduction to promote innovation-led desalination. Ladies and gentlemen, the only expert in the room who would have witnessed the impact of desalination in desalination over the last 50 years is Dr. Miriam Balaban. We should all be thrilled to hear her talk on innovation in desalination, as she's both a pioneer and a historian of the sector. Over nearly 5 decades, desalination innovation has broken barriers of flux, energy consumption, scale, and flexibility, and the market has adapted to new contract and financial models, all resulting in a more affordable solution. The United Nations now recognizes desalination as a reliable, non-conventional source to provide water for all, which is SDG 6. IDA commends these critical changes and transformations and will continue supporting innovative desalination. The partnership with SWIC, a long-standing member of the association, is part of our mission to expand IDA activities with key stakeholders to support technical evolution for a better world. So I invite you to commit yourselves to the material presented here this week with fervent hopes that you will take from here at least one idea that will help to secure innovation in desalination for a water-positive economy and overall global sustainability. Thank you.
Thank you so much, Shannon, for your warm welcome. I was particularly excited by the phrase regenerative water economy. I think that's something we can all aim for. Next, we would like to show you a brief video about this conference and innovation in desalination. Thank you so much.
I can't really think of anything more important to human life than water, and I can't think of a better job than being a scientist or engineer working in the water sector. We are gathered here this week from all over the world to discuss the innovations in desalination that are going to drive productivity and drive improvements in human life over the decades to come.
In order to reduce energy, we need to manage water demand, reduce energy in our treatment processes, and increase our energy self-reliance in renewable energy and biogas.
Transition from thermal to reverse osmosis desalination was a big step in desalination history, and luckily this was led by SWCC since the 80s.
In seawater desalination, we take seawater, after desalinate, we produce fresh water. But in the course, the brine is produced, and so far, right now, what we do with brine is discharge back to the ocean.
For that, we have designed a really innovative system called Microbial Desalination Cell, MDC. This MDC is a bioelectrochemical system where we feed this organic matter to a bacteria who will produce bioelectricity, and with this bioelectricity and through the use of ionic exchange membranes, we are going to desalinate a saline stream, brackish water or seawater, in a single device.
We have expanded our gold standard PX technology to innovate and develop the Ultra PX, which operates at pressure up to 120 bar.
So instead of bringing something in from outside, we'll be producing something in the process. So our goal, where we want to be some decades from now, is essentially zero cost and zero carbon footprint desalination. And that's only the beginning, really. We're going to be talking about innovations for next generation desalination, and we can't even begin to imagine what those will bring.
So our first keynote speaker, who Shannon has already given us a little preview to. I would like to invite Dr. Miriam Balaban to the stage. Dr. Miriam is the Secretary General of the European Desalination Society. She is widely recognized for her lifelong contribution to the desalination industry. A mentor and inspiration to many of us in this room today, we owe her a great deal of gratitude. Dr. Miriam, as she presents on the milestones of innovation in desalination, please do welcome her.
Good morning, everyone. It is a pleasure to see so many people working in desalination and water treatment. There were very few in the beginning, but the industry has grown, the science has grown, and it is really heartwarming to see you all here. Now, the first trigger to my work in desalination was the first International Symposium on Water Desalination in Washington. I wasn't there, but someone who was there told me, a few people who were there told me, you know, there's no journal in desalination. I had studied chemistry at the University of Pennsylvania, but was involved in editing. So I said, I will make one. I will make a journal. And this was the trigger to my entrance into this wonderful industry. And the conference was in Washington, run by the American government, by the US government, the Office of Saline Water and Treatment. Now, the first person that I met at the conference, at the Working Party on Freshwater from the Sea, it was in Athens, is Professor Robert Silver. He's here on the left. I'm next to him. And this was my first entrance into meeting the field, people in the field. Behind us is Zeus. And this was in Athens, at the university. And then there are two other professors with us. Now, another entrance I had was coming to Jubail. Here you have a picture of the meeting in Bahrain, and we flew over then to Jubail to see the beginnings of your great conference, or your great project. The other pioneer is Sidney Lope, who we have here. I published the papers of Sidney Lope. He left them to me before he died. And as we know, he was a founder and one of the main people in reverse osmosis, and which was first worked on in California, at the University of California. There was also some work in Florida. This is Sidney Lope with his colleagues producing the first water in a plant, an actual plant. This is in Coalinga, California. Whereas in the beginning, the technology was first MSF, then it quickly started to go to RO. And this is a graph showing the growth of reverse osmosis of membrane science. These are the 4 journals that are covers of the journals: Desalination and Water Treatment, which I have edited over about 60 years. And of course, I've published thousands of articles, maybe many of them from you here. There was another journal that was begun when Harry Lonsdale said, well, you have so many articles in membrane science, perhaps we should start another journal. And this was the other journal. These are countries, perhaps you can't read the details there, but you can see the growth in the number of countries involved as the list gets longer and longer. And now, actually, in this region, There are more than in North America and in Europe. And the Asia Pacific also has exceeded the number of articles published. Here too, we show the growth in the number of papers. Here we see Asia Pacific is the highest, Middle East is the next. Now, I mentioned that the collaboration and friendship of SWCC, of SWIC, are very close to my heart because you have played a major role in the development. I would like to just go back to Robert Silver, who I mentioned in the beginning, because he was a pioneer from 1956 to 1962. While he worked in the Weir Company, Professor Silver invented the multi-stage flash distillation system. This innovation resulted from a careful analysis of the sources of entropy in various systems for water purification. Today, it is called demineralization. It was a novel idea. The first MSF plant was sold to Saudi Arabia. Bob worked tirelessly to bring it online, sometimes at great risk to his health. It was dangerous to be inside the large flash chamber in the blazing Middle East sun. That plant in Jubail established the commercial viability of the MSF process. The design was duplicated in many places. MSF improved thermal efficiency 2.5 times and made practical the design of very large plants of over millions of gallons per day. Professor Silver was then professor at Glasgow University, where he established a research program in seawater demineralization, where many of Saudis participated. So this is a very brief, just a few little vignettes of what I have experienced. And I do hope to witness the continued growth. I'm also very happy to be a partner in the brine mining, which is now done. Seawater has gone from being a waste to value. Besides providing the very needed water, also now the brine has turned from waste to value and producing minerals which can be used all over the world, industrialized. And here too, I see a long road ahead. So thank you very much. I am very happy to see you all here.
Thank you so much, Dr. Miriam, for your words. And we will now turn our minds to Singapore, a leader in water-related innovation. I would like to welcome Engineer Bernard Koh to the stage, please. Engineer Koh is the Assistant Chief Executive Director of Singapore's National Water Agency, PUB. This morning, he will speak to the topic of Singapore's journey in desalination. Thank you, Engineer Bernard.
His Excellency Abdullah Ibrahim Al Abdul Karim, Governor of SWCC, Your Excellencies, Dr. Ahmad Amandi, Director of DTRI, Mr. Carlos Cosin, President of IDA, Ms. Shannon McCarthy, Secretary General of IDA, distinguished delegates, and ladies and gentlemen. A very good morning to you, and it is with great honor that I'm given this opportunity to share with you today the journey that Singapore has embarked in the area of desalination. For my sharing, I think it is important to put in context the circumstances that Singapore is in as an island state. It has a population of about 5.7 million and a relatively small land area of just 721 square kilometers, with an average daily water demand of 430 mgd, or 1.9 million meter cube per day. Situated near the equator, it receives about 2,200 millimeters of rainfall annually. This seems abundant, but yet we are placed together with several Middle Eastern countries and assessed to be extremely high water stressed. This seems counterintuitive, but unfortunately, it is true. We lack the land mass to contain every drop of rain, and we have no high mountains or large rivers or any natural resource. Water is a scarce resource and becomes an existential issue for Singapore. Recognizing this vulnerability, PUB as a national water agency is tasked to manage the entire water loop, starting from raw water, reservoirs, drainage, and flood control, to water treatment, including desalination, water distribution, wastewater collection, treatment, and reclamation, treated wastewater as new water. We took steps to diversify our water sources and establish our 4 national taps: imported water, water from local catchment, new water, and desalinated water. The 3rd and 4th tab augment Singapore's natural supply. They are less dependent on weather conditions and variance of rainfall. Singapore's desalination journey started in 2005 with the commissioning of Sing Spring Desalination Plant with a capacity of 30 mgd or 136 mld. Over the years, we commissioned more plants, and currently we have a total of 5 desalination plants, with the latest just commissioned in April this year. 3 of the plants are owned and operated by private companies, and the remaining 2 plants by PUB. In a land-scarce Singapore, a 30 mgd desalination plant takes up no more than 3.5 hectares. This requires the plant to be compact, with small footprint, and yet safe to operate and maintainable. An interesting point to highlight in the Keppel Marina is the desalination plant. Besides being aesthetically integrated with a public park, it is a variable salinity plant. That is, it can treat either seawater or fresh water. So when there's rain, the marina reservoir will be full. Rather than discharging the raw water into the sea across the barrage, the desalination plant will draw from the fresh water as its feed source. In times of less rain, perhaps like drought, the plant will switch to seawater. This mode of operation helps save energy. It also helps prevent the growth of barnacles in intake pipelines due to the different salinity of feed water. PUB started exploring this dual mode as early as 2004 as a pilot, scaling up to a demo plant in 2007, and eventually a full-scale plant in 2020. We know that desalination is energy, more energy intensive as compared to conventional water treatment. Currently, the norm it takes about 3.5 kilowatt hour to produce a meter cube of water. PUB aims to reduce this energy consumption to 2 kilowatt hour per meter cube by 2025. Relying on new technologies in R&D, we are exploring a combination of solutions like adopting ceramic UF membranes as pre-treatment, utilizing aquaporin membranes coupled with closed-circuit RO, CCRO, and adoption of pressure-retarded osmosis, PRO. With the increasing threat of climate change and inevitable need to reduce carbon emission, PUB needs to strategically plan and implement measures to ensure a net zero carbon emission by 2050. This undertaking is carried out on 3 fronts: replace carbon, reduce carbon, and remove carbon. Under the business as usual scenario, if we do nothing, we will be seeing about 1 million tons of CO2 equivalent per year in 2050. Therefore, we have started to adopt renewable energy sources to replace carbon from fossil fuel and reduce the energy consumption in our operations. This effort will reduce carbon emission of about 60%. The remaining 40% reduction is achieved through removing carbon. This is done through carbon sequestration. Example is to use alkaline electrolysis technology to convert dissolved carbon dioxide in seawater into solid calcite, which can be recycled as building materials. So moving forward, desalination plants in Singapore will play a critical role in meeting PUB's net zero carbon target. PUB endeavors to lower energy usage in desalination, optimize synergies by co-locating facilities to generate renewable energy sources and recover resources from desalination brine as part of the effort to increase resource circularity. On this note, I will conclude my sharing and thank you for your kind attention.
Well, thank you so much, Engineer Bernard, for your wise words. I always learn something from you, and Singapore's story is so famous. I would now like to turn our minds to the first thematic session and welcome Mr. Thomas Altman to the stage. Mr. Altman, would you like to join us? Thank you. Ladies and gentlemen, we've had a minor delay, and therefore I would like to introduce our first speaker for this session, Mr. Harry Pohlman. Please welcome Mr. Pohlman to the stage.
Assalamu alaikum. Good morning. I'd like to thank the organization of IDA, SWCC and DTRI for the opportunity to present at this conference. The presentation I'm going to give is all about going back to the first part of the desalination plant, that's the seawater intake. I'm going to talk about biofouling and biofouling risks for a Seawater Ro plant, and mainly the risks for the production capacity of a Seawater Ro plant. I'm going to go into a little bit of background on biology, why biofouling, marine biofouling is growing in seawater intake pipes, and I'm going to present results of a case study where we implemented our new technology. When we talk about biofouling, we're actually talking about two different types of biofouling. Biofouling is defined as the unwanted accumulation of micro and macrofouling organisms on substrates which are submerged in seawater or frequently submerged in water. Basically, you got two different types of biofouling. One is microfouling, bacteria. They can form a slime layer, which is generally called a biofilm. The other type of biofouling is marine biofouling, and it consists of shell type of organisms which can settle to a pipe surface. Generally, you're talking about species like mussels, oysters, barnacles. What happens to a pipe when you submerge it in water? When a clean seawater pipe is exposed to seawater, within 1 minute there is already an organic accumulation of organic materials to the surface of the pipe. That forms the basis for bacteria to attach and to settle. Bacterial settlement will happen already within 1 day after the pipe is exposed to seawater. Once the seawater pipe is in the water for several weeks, already the pipe surface is in a condition where marine biofouling larvae can attach and grow to the pipe surface. This will already go within 2 to 3 weeks. You can get fouling, and depending on the seawater temperature and the availability of nutrients, these animals can grow very fast. In the Red Sea area and the Arabian Gulf area, the conditions are very optimal for marine biofouling species. So they can attach very rapidly, but also have a high growth rate. Now, if we look at a Seawater Ro plant, typically at a Seawater Ro plant, the biofouling challenges are at the seawater intake, which is on the right side of the picture. You see submerged intake pipes. There, marine biofouling will generally be able to attach and to create a problem. The other type of biofouling in a Seawater Ro plant is typically on Seawater Ro, on membranes, Ro membranes. Bacterial fouling, biofilm buildup will have a big impact on the performance of the membrane. What is generally done to prevent biofouling, and especially looking at the seawater intake pipes? Well, generally they are procedures which are typically applied at multiple plants, and it consists either of a continuous chlorination or a shock chlorination. Shock chlorination is generally a short period of the day, 1 hour or 2 times 30 minutes, with a relatively high concentration. These dosing procedures are generally applied, and based on after-the-fact observations, they are tuned. The dosing of chlorination is not necessarily focusing on the typical conditions at a specific location. This, in many cases, will result in attachment of marine biofouling in seawater intake pipes. And once this is observed, for example by head loss, precautious measures or measurements to adjust the dosing regime are applied. Marine biofouling in plants and general type of marine biofouling control procedures can put the production capacity and reliability of a Seawater Ro plant at risk. It also increases operation and maintenance cost. If you look at the typical problems at a Seawater Ro plant, if we look at the seawater intake pipe, when marine fouling starts to attach to a pipe, it will increase the wall roughness of the seawater pipe. This means that the seawater pump needs to work harder, more or less, to get sufficient seawater to the RO membranes, to the plant itself. In general, this will result in head loss in the intake basin. Once you face head loss, it can increase the head loss to a certain level that your plant is not able to get sufficient seawater to the plant to produce the amount of potable water according specification. Marine biofouling will also increase the chlorine demand. So if you get fouling, you generally need more chlorine, add more chemicals to the water to reduce the amount of fouling and to mitigate the already settled species. This is all resulting in more cost for the plant. The other type of fouling in an RO plant on the membranes will generally result in an increase of differential pressure. You need a more frequent cleaning frequency. The chemicals you need to use to clean the membranes will increase, and in general, it will increase the cost of the operation of the plant. Another way of controlling biofouling on the seawater intake is called Ecodosing. It's a technology we developed about 20 years ago, and it's all based on taking local specific conditions into account to tune the biofouling control procedure. Local conditions means your chlorination, or another biocide you use, the amount and the time interval you're going to use to mitigate these species is based on the specific biofouling species which are present at a specific location. The seawater quality, seasonal patterns of the seawater, the specifications of the intake seawater plant, but also local environmental constraints. If you combine all these aspects, you can tune your biofouling control procedure in a very efficient way. The method is based on looking at the reactional behavior of biofouling species to a biocide dosing. In general, when you have an oyster, the oyster is open in the sea, filtering water for nutrients and oxygen. If there is a contamination of the water, a natural reaction of the animal is to close its shell and to protect itself. The same happens when you add chlorine to seawater. These animals will close their shell and protect themselves. So a shock dosing does not always result in an efficient control of biofouling mitigation, because these animals just close the shell and wait. Now, if you look at the two graphs, the top graph shows the behavior of a pearl oyster. When there is no contamination in the water, the animal is open, filtering water for food and oxygen. As soon as you start the chlorination, you can see directly the graphs goes to the bottom, which means the animal closes its shell. That goes within a second. Once the chlorination is continuous, they will stay closed and they switch to an anaerobic metabolism and just try to survive. When we developed the technology in the Netherlands, we saw that seawater mussels can stay closed for 10 weeks. So you're dosing a lot of biocide, but the effect on the organism is very minimal. The other interesting thing is when you stop chlorination, these animals open up slowly. And only when they're fully open, they can restart filtering for food and oxygen and recover from the biocide dosing procedure. The ecodosing philosophy is based on adding pulses of chlorine in the seawater intake. Once these animals experience chlorine, they close the shell. If there is no chlorination, they open up slowly again. But just before they are able to recover, you add some more chlorine to the system, another pulse of chlorine. Dosing in that way, you create a behavior you see at the bottom graph. And as you can see, the animals are opening and closing continuously, using a lot of energy, and they get exhausted. So this type of dosing does not use a biocide to actually kill the animals. It's only to trigger them, to make them highly active. They use a lot of energy, and in that case, they will die in a very rapid way. Biofouling control is not necessarily about mitigating and trying to kill adult species. It's all about prevention of settlement of larvae of these species in your intake pipe. The ecodosing method has shown that it creates an environment in your seawater intake which will not allow larvae, when they settle, to get food and oxygen from the water, so get the opportunity to grow into mature species. Now, I'd like to show you one of the case studies we did with this technology. It's the Alfata Seawater Ro Plant in Jubail. The picture on the right top, most of you probably recognize it. It's a top view of the Marafik seawater intake in Jubail. And the Alfata plant is just right next to the intake. The Alfata plant, they started operating and using the seawater from the Marafik intake channel, which was continuously chlorinated. In the first years of operation, they faced many problems on the RO membranes. The cleaning frequency was like every less than 30 days. The membranes became in a very bad condition, and after a couple of years, they decided to switch to a system where there was no chlorination at all. Once they switched, the cleaning frequency was postponed to every 3 months, but after a couple of years of operation, they saw that there was marine fouling in the seawater intake pipe. Also, they saw attachment of, for example, barnacles in the DMF filters. Alfata decided to build a new seawater intake, which you can see on the right side of the top picture, to have a separate seawater intake which they could control themselves. We were contracted to come up with the specifications for this new seawater intake with 2 objectives: prevent marine fouling in the seawater intake system, and at the same time preserve the RO membranes, so not increase the biological fouling on the RO membranes, to maintain a cleaning frequency of every 3 months. The plant is running now for almost 5 years on this dosing regime. It was implemented in September 2017, and the results we saw is 2 things. At the seawater intake, and the pictures on the right side show the rotating drum screen, the seawater intake is clean. There is no marine fouling attachment. There is no head loss measured. The intake structure is fine. Also in the DMF filters, there was no marine fouling attachment found anymore. At the same time, what they observed is that the RO membranes perform very well. The cleaning frequency actually has been further postponed to almost every 5 months now, compared to the period of non-chlorination. So the post-chlorination, meaning a low concentration of chlorine required, because the concentration of chlorine in your seawater intake can be very low, because you only need to trigger the animal to close its shell, so you don't need to kill the animal. This, in this case, resulted in a very optimal plant performance, a postponed cleaning frequency, and a clean seawater intake. Some final remarks on this technology. Well, it is well known that it's a challenge for seawater RO plants in many locations around the world to find the right balance between marine fouling at the seawater intake and bacterial fouling on the RO membrane. How do you design your seawater treatment right at the beginning of the plant, not affecting the RO membranes? That's in general a big challenge. The results we saw at the Alfata plant showed that it is possible to get into a balance and to get a long-term field experience based on this technology. At the moment, we installed this technology at 5 seawater RO plants. We are doing a project at the moment in Saudi Arabia at another plant to design the specifications for seawater treatment based on this technology. The 5 RO plants which are using this technology are spread around the Gulf region in Oman, UAE, Qatar, and Saudi Arabia. At some locations, we saw that the amount of chlorine used at the seawater intake is very low, as mentioned, but also resulted in the fact that they don't need to use any sodium bisulfate to neutralize chlorine after the pre-treatments, pre-filtration. This is again a cost benefit and also beneficial for biofouling on the RO membranes. It is important to always tune your seawater treatment based on local specific conditions. So a copy-paste of a dosing specification will not necessarily result in a proper effect. Algae blooms are a specific phenomena which are observed by Seawater Ro plants, and algae blooms, algae by itself are chlorine demand. The chlorine you add to the seawater intake is generally consumed by the algae. So my thinking is always that if you add chlorine to the seawater intake, the only objective of adding chlorine to the seawater intake is to prevent marine biofouling based on a certain level of FRC, free residual chlorine. If algae consume all the chlorine in the seawater you added, and there is no residual chlorine in the seawater, then the objective of adding chlorine is more or less not applicable. At the same time, oxidizing algae could result in unwanted products, which could also result in feeding and increasing biofouling on the RO membranes. My last comment on this topic is, well, I'm talking about chlorination because chlorination is still the most applied biocide for marine biofouling control. However, the technology we used for a lot of different type of biocides in different type of applications, and the principle of the technology works very well. It's all based on how do these animals respond to a dosing of a certain biocide. At the moment, other technologies can be used and are considered to use for seawater treatment. Now, one of them is, for example, ultra-pure chlorine dioxide. It's an interesting and promising biocide to overcome some of the disadvantages of using chlorine. A last slide I'd like to present, which is a little bit off topic, but also on topic, because it's a biological risk for Seawater Ro plants. In the past, we saw utilities, power plants, oil and gas plants, which were facing operational problems due to a jellyfish bloom. Jellyfish, when they arrive in large amounts at your seawater intake, they could overload your screening, which could actually block more or less and prevent seawater entering to the plant. Worst case, they could result in a plant outage. In 2019, August 2019, the Sea of Oman was facing a major jellyfish bloom. This resulted in a big challenge for many of the industries along the Omani coast and also the coast around Fujairah in the UAE. And some of the plants actually tripped. They had an unplanned shutdown because of the amount of jellyfish which arrived at their seawater intake. Based on our experience with jellyfish, we were contracted and we did some research in how can you prevent this kind of event and secure operational reliability of your RO plant. Prevention, the conclusion of this work and these studies are all based on three things you need. One is you need an early warning. So you need to have a heads up, an early warning, when do the jellyfish arrive at your seawater intake. At that moment in time, you can take precautious measurements, for example, reducing the amount of jellyfish actually arriving at your seawater intake pipe and at your screening. It's not about full prevention of ingress, it's all about reducing the amount of jellyfish arriving at your screening. And that's the third point, optimizing your screening operation to be able to handle a certain amount of biomass of jellyfish. The combination of these three, that could help you to prevent operational risks for jellyfish. I'd like to thank you for your attention. Thank you.
Thank you so much, Mr. Polman, for that excellent presentation. As we continue on with our first theme, breaking the cost and energy barriers for desalination, I am very pleased to introduce our chairs and co-chair for the session, Mr. Thomas Altman, the Executive Vice President of Aqua Power, and Dr. Seung Young Kim, Professor at Kyungnam University, South Korea. Thank you, gentlemen. You have the stage.
Good morning, ladies and gentlemen. I have the pleasure to introduce the next speaker. The next speaker the second speaker for this session is Mr. Atman Shah. He is the Business Development Director from Nanostone, located in Dubai. Nanostone has a great experience in the field of pretreatment with a new technology, and I am welcoming Mr. Atman Shah to the stage. Thank you.
Thank you, Thomas. Good morning, ladies and gentlemen. I'm going to be talking today about ceramic membranes, ceramic ultrafiltration membranes for the pretreatment of seawater RO. As you most know, seawater RO operations always rely on robust pretreatment. Provided that the RO membrane feed is free from suspended solids, particulate matter, and organics, RO membranes can typically serve up to 2 years without doing intensive cleaning, with a potential lifetime of 10 years. Conventional pretreatment technologies, owing to the poor seawater quality deteriorated over the years, have really suffered in maintaining capacity, requiring extensive cleaning and frequent RO element replacement. The polymeric ultrafiltration membranes was typically used and implemented to address these shortfalls and challenges. The seawater today offers unique challenges which now require alternative pretreatment schemes. The quality of seawater in terms of suspended solids, organics, frequent algal blooms have really impacted facilities all over the world. The conventional ultrafiltration membranes tend to allow or pass through dissolved organics, and these are really a potential source for downstream RO fouling. At peak water quality or during algal bloom events, the conventional UF is unable to maintain capacity because the flux has to be lowered to reduce the fouling potential. The hollow fiber-based polymeric UF is always susceptible to fiber breakage and therefore allowing pass-through and not being an effective pretreatment barrier for RO. Poor water quality has, as I mentioned, affected plants globally, reduced capacity, high downtime, and of course, a frequent RO replacement. Existing incumbent pretreatment processes like DAF, gravity media filters, typically come about with their own unique challenges. Large footprints, expensive to construct, and of course, significant risk of carryover to RO. The Nanostone ceramic ultrafiltration membrane, with a unique configuration and membrane design, eliminates the need for DAF, dual media filtration, or even clarification steps, which are typically required upstream of the RO. This can not only optimize the pretreatment operations, but also reduce the complexity of having multiple pretreatment steps. The membrane, which is an aluminum oxide extruded material, has a 2.4 millimeter feed water channel with a 30 nanometer or 0.03 micron absolute pore size cutoff. We apply nanoparticles on the surface of the membrane, which gives us this even pore size distribution. With these wide feedwater channels and the nanoparticle coating, we are able to handle a high concentration of suspended solids, particulate matter, without the need for DAF or media filtration. We've been working extensively in Singapore with PUB at Tuas test bedding facility, the multiple facilities, and looking for something which is more robust and reliable for the downstream RO. Our pilot demonstration system has completed a one-year operation, and the results have been extremely encouraging. The seawater quality often deteriorates, seasonal changes, turbidity, organics, and by applying inline coagulation with ferric chloride upstream of the ceramic ultrafiltration process, we could achieve an organic content removal of up to 60% at enhanced coagulation. We did see a surge in the TMP by reducing the pH to about 5.5 by achieving enhanced coagulation, but also the TMP was much more stable at a sweep flocculation, was about pH 7.5. The optimal dosage for ferric chloride was found to be about 4.5, 5 ppm, beyond which point we did not see an increase in the organic content. We've tested at different fluxes, and remember, we don't have any upstream pretreatment. It is direct intake filtration with our ceramic ultrafiltration. And having tested at different settings and fluxes, we found 250 LMH as the chosen flux for demonstration. We started the run with 150 LMH, during which we had an algal bloom, and the membrane recovered without doing any intervention or offline cleaning in place. Because of the unique design of the membrane, we are able to extend the production cycle or the filtration cycle to as high as 90 minutes, even during peak water quality. And we can do so while maintaining a flux of about 250 LMH with a recovery of 98%. And even during the peak water quality, we could maintain an outlet SDI of less than 2 and turbidity less than 0.05. The chemical backwash was optimized, so we have to carry out one chemical backwash every 24 hours and delay the CIP to just once every 3 months. This incorporates the peak water quality during the algal bloom events. When we ramped up the flux to 250 LMH, during the month of March, we had a severe algal bloom. The chlorophyll A meter read about 60 parts per billion. And as you can see, the dark blue, the KPA delta P marginally increased to about 100 KPA. And then by doing a simple chlorine backwash, we could restore the permeability. The membrane, because of the unique material, aluminum oxide, allows tolerance to oil as well. Marine oil was injected upstream of our membrane to the dosage of about 1.2. And as you can see, the cleaning requirement due to oil was delayed up to 2 weeks. In other words, it was not instantaneous fouling occurring due to the oil levels. The second case study is an Aqua Power nanostone joint pilot, Barka 1, Oman, an existing Seawater Ro facility, taking water from the Gulf of Oman. Again, due to the poor water quality, frequent algal blooms, the existing plant had flux reduction issues, productivity issues, and we tied up with Aqua Power to demonstrate that the ceramic ultrafiltration process can be a solution without implementing incumbent solutions like DAF. There were several parameters or objectives, obviously in addition to being a reliable and dependable pretreatment solution, to actually monitor the long-term performance in terms of cleaning frequencies, outlet water quality, to determine the suitability for the existing downstream RO, and then eventually provide a full-scale information for the facility. Gulf of Oman, as most of you know, is very challenging. Peak water qualities are often seen, and our optimization protocol had different flux regimes, different chemical frequencies, coagulant dosages as well. We've tried 225 LMH, 200 LMH, and we've found 225 LMH as the critical flux, owing to the fact that the water quality often deteriorates from time to time. And one of the demonstration criteria was to produce full capacity of the system at all times. So while 225 LMH was encouraging, the optimal flux was much, much lower. But we did see some stability at 225 LMH, 200 LMH, and so on. Eventually, for the long-term evaluation, for the long-term performance, we found that 150 LMH was optimal, steady-state performance. In the end of March, beginning of April, we had a severe algal bloom, and there was a surge in TMP simply because we were not able to dial in the coagulation, inline coagulation, ferric chloride. But had we had proactive measurement of chlorophyll A levels, we could have done that. And by dialing the coagulation at about 6 ppm at a pH of about 7.5, we could restore the permeability without having to do a CIP. It is important to mention that this was just tuning in response for the peak water quality algae bloom, that is by adjusting the coagulant. But it is not the case that such a high requirement of coagulant will be applicable to normal seawater conditions, because there would be cases when the coagulant dose will be much, much lower than 8 ppm. The pilot system operated at full capacity during peak water quality. There is high flux, high recovery, and eventually leading to high availability of pretreatment. This not only reduces the capex and footprint savings, but also optimizes the overall energy pattern of the system. Organics can be removed potentially up to 70% based on pH adjustments, and we can also remove oil and grease. Thank you very much.
Yes, thank you, Mr. Atman, for this presentation for an advanced pretreatment system which has a big potential. So we had two presentations now. Before the coffee break, I will open the floor for any questions. We have time for about 3 questions. So please raise your hand if you want to address any question. So while people are thinking about the question, Mr. Atman, can you explain how does ceramic membranes behave during periods with difficult seawater like algae blooms?
Thank you, Thomas, for the question. There are a couple of aspects which help contribute to handle the peak water quality. The 2.4 millimeter feed water channels allow us to handle a high concentration of physical algae cells, suspended solids, and particulate matter without the need for DAF. Also, because of the 2.4 millimeter channels are across the length of the membrane, they allow us to have extended filtration cycles as high as 90 minutes with reduced cleaning frequency. So the suspended solid retention is extremely high. That's one. Second is that the inline coagulation, which is dialed in upstream of the ceramic UF process, tends to bind and form a pre-coat layer on the membrane of the surface. And this is extremely important because this allows to form a barrier between the incoming organic suspended solids, algae cells. So this is the barrier between the incoming pollutants and the surface of the membrane. So the combination of the engineering aspect and the dialed-in coagulation allows us to handle suspended solids, algal bloom cells, and of course, organics much more effectively than other pre-treatment processes.
Thank you. Thank you very much. Are there any more questions? There's one question on the back side. Can you go to the microphone, please?
First, I'd like to thank you for the interesting presentation. My question about...
can you please say your name and affiliation first,
yeah.
And then the question? Yeah. Thanks.
My name is Dr. Marwa Shalabi, professor in the National Research Center, Chemical Engineering Department in Egypt. My question about a country like Singapore have a leading technology in desalination, and so seeking for economic solutions for pre-treatment. What about the initial high cost for the production of ceramic ultrafiltration membranes? Thank you.
Thank you for the question. As you've seen from the treatment schematic, the ceramic UF process allows the elimination of upstream processes like DAF, media filtration, micron filters, and of course, cartridge filters as well. So this allows the upfront capital expenditure to be optimized significantly as compared to the incumbent process. That's one. The CAPEX is taken care of. On the long-term evaluation, the long-term OPEX, your energy pattern can come down, your energy demand can come down because the DAF does not have to be operated all the time. And subsequently, we also offer a 20-year lifetime warranty, so the membrane does not have to be replaced for the entire length of the project. So those 2 or 3 aspects allow us to be much more competitive and therefore be the lowest water cost solution for desalination projects.
And the final question, please. Here's one gentleman in the 3rd row. Can you please bring a microphone? Okay.
Good morning. My question to Mr. Balaban. Nice to meet you. My question, there are two parts of question. For jellyfish, what I understand from your presentation, there is no technology could resolve the problem at all, just mitigation and take some measurement in order to reduce the risk on the plant. This is for question. Is there any technology can be provided and implemented in the plant, existing plant, to overcome this problem? Second question, for your chlorination dosing system, for the existing plant, what is the requirement in order to implement the idea what you implement? And what is the effective of that from your, based on your experience in the small plant, Al-Fatih plant, for the huge plant, million cubic meter or more than million cubic meter? Thank you.
Thank you, Dr. Srani. Getting back to your first question, I agree with your statement. There is no solution for jellyfish. It's a phenomenon which arrives, typically very unexpected, and the approach you can follow is to try to prevent the amount of jellyfish actually arrive on screening. And to prevent it, there are some technologies, physical technologies, mechanical technologies, which could divert, for example, jellyfish from a specific intake to at least reduce the amount of jellyfish arriving at a screen. Chlorination, your second question, chlorination has no effect whatsoever on jellyfish or any chemical treatment. These animals typically go with the flow. So they arrive, and with the seawater flow, more or less, they enter a seawater system. As mentioned, what is important is an early warning, and that's based on the studies we did. There is no real early warning with a good track record, more or less, a long track record for jellyfish. For algae bloom, it exists. For jellyfish, it's more challenging. However, we are working now with an early warning system, which has proven to be effective, but it's more in the area of South America, and that's a technology we are now trying to trial in the GCC region. To get an early warning, which is important, the next step is the deflection of jellyfish. Well, to prevent ingress, there are methods available which could reduce the amount of jellyfish. For example, air bubble curtains, nets, those kind of systems are used. The system itself needs to be designed based on the typical type of jellyfish you get at your intake, for example, in the Jubail area. What we noticed in previous projects we worked in, for example, in Ras Laffan, there was a major jellyfish bloom in 2009. Those jellyfish were typically very small and slimy, while the ones we noted in Oman in 2019 and 2020 were relatively big, but also very stiff and quite heavy. So, for example, if you would design an air bubble curtain system, you need to take into account the typical type of species which you actually try to divert from your intake. And the systems, what we saw, it will not prevent 100% ingress or jellyfish arrival on your screen. That's impossible, but that should also not be the objective. I personally think it's more about reducing the amount of jellyfish to a certain amount of biomass which your screening can handle. So the combination of those things, that could be the solution, more or less, or solution that will help you at least to reduce and to prevent the risk of jellyfish overloading a screen. Coming back to your second question, the pulse dosing, the ecodosing technology in existing plants. Well, we implemented this technology now for more than 20 years in all different kinds of utilities, using seawater or fresh water for cooling or for production of potable water. Typically, the change and the adjustment required is if you already have a chlorination system and an electric chlorination plant, what will be the adjustment is your dosing strategy will change because you're dosing intermittently chlorine to your seawater intake. And the way we change the system is to bring the electric chlorination plant into a new mass balance. So based on the study and based on the knowledge of how much chlorine do you actually need to dose at your seawater intake, we calculate the required capacity of electric chlorination, how much chlorine do you need to produce in a certain time period. And the intermittent dosing is typically followed by a seawater flush through your dosing pipes. So what we noted in previous projects is that there is an additional benefit of this technology, is that when you add chlorine to a seawater intake and you're flushing in between the pulses of chlorine with seawater, you actually reduce the risk for scaling in your seawater pipes, and scaling from calcium magnesium hydroxides, the byproduct of electrochlorination. The adjustment is, as mentioned, it's like a three-way valve after your degassing tank, making it possible to switch between chlorine and seawater. And it's generally a minor change to the existing utility.
Thank you very much. I think our time is elapsed. This brings us to the end of the part one of this pre-treatment session. And applause for the speaker, please.
Thank you so much. Thank you so much, Mr. Altman, and to our distinguished speakers this morning, and for your kind words about the desalination sector. If I could ask you to please make your way back to the audience. Thank you so much. And as we turn our minds again to innovation, which is the theme of our conference here, we also think about how we can collaborate and participate together to maximize the benefits and outcomes from that innovation. That is why now we will have some exciting signatures on agreements between important institutions here in the Kingdom. Therefore, firstly, I'd like to introduce the first Memorandum of Understanding that will be signed today. It will be between the Saline Water Conversion Corporation, SWEC, and the Ministry of Industry and Mineral Resources. The objectives of this MOU are to enhance investment opportunities in the industry, to create smart databases for desalination materials, and to study and develop the construction of factories. Firstly, I would like to welcome to the stage His Excellency Engineer Abdullah Ibrahim Abdul Karim, SWEC Governor. Thank you so much. Also, to welcome to the stage, I would like to invite His Excellency Engineer Osama bin Abdulaziz Al Zamil, Deputy Minister of Industry and Mineral Resources. Congratulations to both institutions on this great new partnership. Secondly, I would like to introduce the service agreement between the Saline Water Conversion Corporation, SWEC, and the Saudi Irrigation Organization. The objective of this service agreement will be to promote innovation solutions for desalination of saline water for irrigation purposes. Therefore, I am pleased to keep the Governor, His Excellency, on the stage, and also welcome Dr. Fuad Ahmad Mubarak, President of the Saudi Irrigation Organization. Again, congratulations to both organizations on this great new partnership. Last but not least, I am pleased to introduce a Memorandum of Understanding between the SWEC Water Conversion Corporation, the Saline Water Conversion Corporation, SWEC, and Donora Water Technologies. To sign this on behalf of SWEC, I would like to welcome Dr. Ahmed Al-Amodi, Executive Director of Desalination Technology and Innovation Research Institute, to the stage. And also welcome Dr. Mirka Waldera, CEO of Donora Water Technologies. Congratulations to the institutions on this great new partnership that I'm sure will continue to drive innovation in the desalination sector. Ladies and gentlemen, thank you for your attention in the opening part of today's conference. We will now have a coffee break and resume at 10:30 a.m. Thank you so much. Ladies and gentlemen, I hope you enjoyed your coffee break. I invite you to take your seats as we proceed with the program. Just a small announcement before we go on. I'd like to remind you that the workshops are happening simultaneously throughout the program, throughout the 3 days. Starting at 10:30 today, that is starting now, there is a workshop called Enabling Research and Innovation in the Science Lab, happening on the first floor in room Jude 2. If you so wish to attend, please make your way there now via the escalators, the elevator, around to your left near the ATM. For those of you who would like to remain with us for this next part of the program, I'm pleased to let you know that we will be continuing on with the first thematic session in phase 2. And therefore, I would like to invite to the stage one of our co-chairs of the session, Dr. Seung-Hyun Kim, professor at Kyungnam University, South Korea. Thank you so much.
Morning. We'll resume this morning session. We still have 3 papers before coffee break. And the first paper is about cleaning in-place system for cartridge filters and Ras Al Khair's power and desalination plant. It will be presented by engineer Abdul Rahman Abu Taleb. He's a senior engineer at DTRI at SWIC. Please welcome Mr. Abu Taleb.
Assalamu alaikum. Good morning. It's a pleasure to be here. First of all, I would like to thank the organizers, SWCC, DTRI, and the IDA, and all the attendees for being here today. Today, I will present clean in-place system for cartridge filters fizzle or Ras Al Khair. First, Ras Al Khair desalination plant is a hybrid plant that contains emissive and RO technologies with a capacity of more than 1 million cubic meter per day. The emissive produces around 700,000 and RO produces around 310,000 cubic meter per day. Ras Al Khair plant is located in the Ras Al Khair industrial city in the Arabian Gulf, northwest of Jubail. Actually, the main reason for the CIB system is to modify the current practice of replacement of cartridge filters element or Ras Al Khair. Now, usually they are replacing the cartridge filter elements each 3 months, and by doing the CIB, we want to increase the lifetime of the cartridge filter by minimizing the differential pressure and increasing the flow rate, the average flow rate per each fizzle. This is my agenda. First, I will show a schematic for the Ras Al Khair SWRO desalination plant. In addition to Ras Al Khair cartridge filter fizzle, then I will show our system for the CIB. Later on, I will start with the result of the pilot testing for the cartridge filter as well as the CIB system. Then I will show the impact of the CIB in terms of water quality and the differential pressure in the line A fizzle. Finally, I will show the outcome for the CIB system on the lifetime of the cartridge filter elements and the average filtered water by each fizzle. This is schematic of the Ras Al Khair desalination plant. As we can see in the SWRO, there is 2 lines. Each line consists of dissolved air flotation system, followed by dual media filtration system, then a cartridge filter, and SWRO and BWRO membranes, finally a post-treatment. This is the Ras Al Khair cartridge filter fizzle. Totally, there is 31 cartridge filter fizzle Ras Al Khair. There is 15 plus 1 standby in line A and 15 in line B. Each cartridge filter fizzle contains of 421 cartridge filter element with filtration rating 10 micro absolute and average flow rate by each fizzle 1,400, and it can go up to 1,650, which is the maximum flow rate for each fizzle. and the maximum now, and also in each line, it has a pressure transmitter in the inlet and the outlet of each line, and the maximum differential pressure before initiating any replacement for any cartridge filter is 1.5, and whenever it reaches 1.5, the operators of Ras Al Khair will ask the maintenance to replace any cartridge filter, and therefore DTRI has initiated a CIB system to extend the lifetime by doing a low pH cleaning, which will remove the ferric, and followed by a flushing system, which will remove the particle. Mainly, the differential pressure causes increasing in any plant in the world is caused by ferric and the particles. This is a clean in place diagram. We have two systems. One system in line A and the second in line B. Each system consists of two tanks, two pumps, and connections to the cartridge, all the cartridge filters fizzles in the same line. And as you can see, the CIB system is connected to the outlet of the filtered water fizzle, which will be the inlet for my CIB system. Also, in each line, there is a safety eye shower and connections to all fizzles. This is the actual CIB system. As you can see, there's two tanks, and the capacity of each tank is 5 cubic meter, and there's two pumps. The left pump is for sending the solution, feeding to the cartridge filter fizzle. The right pump is for suction the solution from the cartridge filter fizzle. And now we will talk about the procedure for the CIB. First, we will start with the cartridge filter isolation. We will do a partial drain followed by a full drain to remove the particle in the middle and at the end. Then we will prepare the acid solution. Here we use for these two tanks just 1 liter or 950 milli of hydrochloric acid with 37% concentration. And we circulate it in the two tanks by adding the surface water. And after circulating in the two tanks, we will measure the pH. Usually, the pH will be around 3.5 based on the calculation. When we get 3.5, we will start the cleaning process. The cleaning process will start with using the left pump to feed the solution to the current cartridge filter fizzle, and we will return it by the right pump, and we will repeat this step 3 times. In the 4th time, we will keep the acid solution soaked inside each cartridge filter fizzle for 24 hours. After 24 hours, we will return the acid solution, and we will measure the pH again. Usually, the pH will range about 5.5 to 6, which is sure that for us, there is a chemical reaction happened inside each cartridge filter, mainly the pH incremental due to the ferric chloride inside the cartridge filter elements. After 24 hours, as we mentioned, we will do flushing for the current cartridge filter fizzle, and we will return the cartridge filter to the surface, and we will close the CIB system. Before doing this, initiating this system, we did a biotesting. The biotesting, we harvested, as we can see in the left picture, this is a cartridge filter elements, and there is 421 of it in each fizzle. So we harvested 5 used, and the brown color is the ferric chloride, and the left one is a new one, white, which when it's new. So we harvested 5 used and 1 new, and we soaked them in acid solution at a pH of 3.5, and we cleaned them with a hose to simulate what will happen in the actual CIB process. And we soaked them again for 12 hours. After 12 hours, after we harvested from the cartridge filter fizzle, we drained them for 15 minutes, and we measured the weight. Then we soak them for 12 hours. After 12 hours, we flush them with the clean water, and we measured the weight again. We found out that the weight loss is 85% of the initial weight. This is the first bar chart result for our CIB system. As we can see, we selected 4 fizzles, 2 in line A and 2 in line B. The 2 in line A after 2 months of using, and the second 2 after around 1 month of using. And we compared the flow rate before the experiment and after the experiment. So as we can see, the flow rate before the experiment was 500, after the experiment around 600, so it increased by 20%. For the second experiment, which is for unit A12, it increased by 15%. And for line B, as we can see, since it just has 1 month in operation, it increased by 11% for the B3, and for the B13, it increased by 22%. And this is show that the CIB has enormous impact on retaining the efficiency. The main goal of this, this experiment is we want to know if it's going to work if we did it more than one time or no. So we selected A3 and A5, and we repeated the experiment more than one time. For the first time, for the A3, the flow rate increased by 15%, and we did it again for the same filter after 118 days, and increased by 12%. And the circle above it is the percentage recovery, which means that the flow rate after the CIB divided by the maximum flow rate, which is in the red dot, which is equal to 1,650 cubic meter per hour. And for line B, it increased by 14%. The second time, it increased by 22% after 127 days. Usually, the current practice, Ras Al Khair, they are replacing the filters each 3 months. And after the CIB, we increased the lifetime up to 134 days. During the CIB, we want to know if there's any negative impact on the filtered water quality or not. So we compared, we measured the SDI and the turbidity, and for the two fizzle that I did the CIB on, which is A3 and A5, and we compared them in the same header, which contains around 13 Cartridge filter fizzle, and we took the average. As we can see, the blue dot is for the average in the Ras Al Khair plant, and the black and red, it's after the CIB. There is incremental in the CIB, however, it's still below the range. Our maximum range is 4. Whenever the SDI reaches 4, we are going to replace the filter. So we have increased the lifetime up to 134 days. After that, if we observe any incremental in the SDI, we will replace it. Also, we measured the turbidity for the average line A compared to the A3 and A5, and we can see there's a slight increase in the turbidity. However, the value for the average line A average is low because Ras Al Khair, they replaced most of the filter are new, so we cannot make sure if it's have negative impact or no. Here we measured, since we don't have a delta B in each Cartridge filter fizzle Ras Al Khair, we just have in the inlet and the outlet of the transmitter. So we measure the delta B decreasing after each CIB. As we can see, the 3 circles here, which means that the delta B in the all header, which contains 16 Cartridge filter fizzle, has declined after each CIB. Another fluctuation in the graph is caused by the replacement of Cartridge filter Ras Al Khair, since we don't disturb any operation conditions, and we can see that it has a big impact on the minimizing the delta B, which is the main indicator of Ras Al Khair. As we mentioned before, when the delta B reached to 1.5, the operator Ras Al Khair will ask the maintenance team to replace any Cartridge filter with the highest service duration. Here we compared how much with the CIB, how much we increased the average filtered flow rate. So we can see with the CIB, the flow rate, the amount of filtered water for one cycle. One cycle means when we replace it until we replace it again, and increased by 42%. And this is the lifetime, which is very important for us. The lifetime increased by 51%, and with the CIB for the average for A3 and A5, as we can see here, the lifetime increased to 134 days. And for the remaining filter, it's around 3 months, 89 days, which is the average of the remaining filter for each cycle, when we replace it until we replace it again. In conclusion, the cost saving usually comes from the saving in the cartridge filter replacement. As based on the calculation, we replaced annually around 52,000 cartridge filters element. And since minimizing the replacement period and extending the lifetime, the cost saving for in Ras Al Khair was $109,000, and the lifetime increased by 51%, and the filter water increased by 42%, and the initial investment, which is the cost of the two systems, one in line A and one in line B, it just cost $34,000. And since we are using just 1 liter of hydrochloric acid for each CIP process, it costs annually for the all filters in the, if we calculate, if we did it 4 times for each cartridge filter fizzle, it's gonna just cost each year $111. I think I'm done.
We have plenty of time for questions. Do you have a question? If you have a question, please raise your hand and identify yourself by saying your name and affiliation before addressing questions. Any question? Yes, please. Please hand over microphone.
Thank you, Abdurrahman, for this nice presentation. My question is, if I understand right, you said that there is increasing in the turbidity of the filtrated water.
Yeah.
Do you have an explanation for that? And the other question is, did you do any full analysis, chemical analysis for the filtrated water to compare?
Can you repeat the second question?
The other one is, did you do any full chemical analysis for filtrated water? You measure turbidity and you measure, I think, it's the eye.
Mm-hmm.
So why did you not do the full and chemical test for filtrated water?
Yeah, for the first questions, yeah, there's a slight increase in the turbidity, and maybe because the increasing the lifetime. Whenever we reach above 134 days, we should monitor the turbidity. Usually, but the main factor for us is the SDI. Since as we know, the maximum SDI we should get before the RO is 4, so we focus in the SDI, and the turbidity, I think it's because the lifetime, and we have to monitor it, especially after 100 days. If we reach to a limit that we cannot, the turbidity is very high, okay, we should replace this filter. And this is the two parameters is our indication. And for your second questions, we measure the pH after the chemical cleaning, before 3.5, after 5.5, so which means that there is no like very low pH inside the cartridge filter. And we didn't need to do the chemical analysis because we are doing the flushing. As I mentioned, for each cartridge filter, we will do a flushing with the surface water. So when we do a flushing, and we already increase the pH to above 5.5. So we are on the safe side in here.
Any other questions? Yes, over there. Please. Yeah.
Yes. Hello? Excuse me?
Yeah.
My name is Islam from Metito. Thank you for the nice presentation. I would like to ask you if during this trial, did you make any tests on the microfibers effect on the elements, considering the sieving test of the element after the CIP? Is it impacted something like beta number of the element itself? You mentioned that these elements are 10 micron absolute. Is there any impact on this? Because in one of the figures I can see in the third CIP, the recovered flow rate is increased than the nominal initial of the filter before the CIP.
So the contaminant is each cartridge filter element is different in each cartridge filter, so it will not be the equally. So we saw that in each cartridge filter fizzle, the incremental of the flow rate is different. So we observe by visually the cartridge filter elements after using for a long time. We didn't see any great impact. However, we just focus, as we know in the WRO, the main factor for us is the SDI. So we just focused on the SDI. Whenever reach to a limit, we can say there is like deformation in the element, but we didn't exceed 4, which means we are on the safe side. However, we are planning to increase the lifetime more than 134 days. And for the next system, we have around a new system in different plants. We will start in it next week. We want to see how much limit we can like get to 150 days or higher than that. And we can do like extensive study if it's gonna impact, there's any critical impact on the element itself or no.
If you can, please, can you bring the figure so I can explain my point?
Excuse me, this one is not working.
Okay.
The figures are not, anyone here?
I think we have some technical problems. Can you, perhaps you can talk later after during the break. We have still one more question to address, okay?
Firstly, thank you for your presentation, it's very nice. I think the increase in the lifetime is a promising data, but I'm asking about changing the path for the water as a backwash. Have you made this, or you are going in the main filtering way for the cartridge?
So as I saw in the diagram, I said the feed for my acid solution is the outlet of the current cartridge filter. The outlet to the RO is my feed for my system.
Yeah.
And this
is the backwash.
Yeah.
Okay. Thank you.
Any other questions? Yes.
Thank you, Abdurrahman, for your talk. So I'm Ratul Das from EcoPower. I have a question, and the question relates to the lifetime of the RO membranes. So as you might know, the cartridge filters are the last line of defense for the RO membranes.
Yeah.
And when you regenerate a cartridge filter, the water quality of the filtrate is inferior compared to a newer membrane. So when you do a cost-benefit analysis, you should do a cost-benefit analysis of the RO membrane itself.
Can
because
you increase the volume?
When you do a cost-benefit analysis, we should know what's the impact of fouling on the membranes because of inferior water quality. Because this will increase the cost, because as we know, cartridge filters cost pennies compared to RO membranes itself. Any comment on that?
Yeah, we are investigating actually a high pH cleaning. And we have done it before for the dual media filter. And usually when we smell any like fishy smell in the cartridge filter filter, this will show us there is organic issue. And we are planning to do high pH cleaning, but it's not like in the Arabian Gulf Ras Al Khair plant, because we didn't observe this issue, but it's available in other plants. So we are trying to do a high pH cleaning, and we will see the outcome of it. And in the terms of the RO, we didn't investigate the RO. We just focus on the SDI value before going to the RO.
The thing is, the data you showed, the SDI of the filtered water quality after regeneration is a little higher than the
Yeah, for sure.
Right?
And this is the reason, actually, the reason for that. More than 65 or 70% of all the filters are new. So in the Ras Al Khair, they will continuous operation, they will change the filter. So it's new compared to so we cannot have a clear result about the impact, since we don't want to disturb the operation in Ras Al Khair. So whenever they will change any cartridge filter fizzle, we are not going to disturb that. We just focus in the final whenever, and we have a limit. When we will get above 4, for sure we are going to replace it.
All right, thank you.
Sure.
Any other question?
Yes.
Okay.
This Engineer Abdullah Bladi from DTI. Just have a question about the organic load. Now, you know, the cartridge filter usually have some sort of organic content. So have you did any analysis after the cartridge filter regarding this organic? Because this will cause biofouling in the membrane. You get the question?
As you know, the size of the cartridge filter is 10 micro, and it's going to remove mainly the solids. So usually the organic load you can remove in the, you cannot like remove by the cartridge filter. You will, it's going to be removed in the membrane. So we have no, you have no control on it in the, when it's come to the cartridge filter.
I think time is up. Okay. Okay, thank you. Thank you, Mr. Abdul Rahman, for your nice presentation.
So, thank you. We are moving now to the fourth paper in this session, which is about innovative backwashing system of dual media filters. And this presentation will be conducted by Dr. Park from DTRI SWCC. Please welcome Dr. Park to the stage.
Good morning. Assalamu alaikum. From 2019, DTRI conducted operation and maintenance improvement project in Laci Desalination Plant. Today I will introduce innovative backwashing system of dual media filter. In the Middle East, dual media filter is the most commonly used pretreatment process of SWRO desalination plant. Right figure shows the location of SWCC desalination plant. SWCC has 17 desalination plants in the kingdom. SWRO plant in Laci have single-stage gravity-type dual media filter. But in case of Arabian Gulf Sea, dissolved air flotation has been installed with dual media filtration to remove harmful algal bloom or oil and grease. Al-Khafji plant consists of DMF and ultrafiltration. This slide shows the processes of Laci desalination plant. It is hybrid processes of summer and RO. It consists of 8 units of MSF evaporators and 2 lines of SWRO processes. Each SWRO process consists of dissolved air flotation, dual media filtration, cartridge filter, seawater RO, and brackish RO. Plant capacity is 1,050,000 cubic meters per day. MSF produces 70% of total water production, and RO is 30%. From now on, I will explain backwashing system of DMF filter. In these slides, you can see the conventional backwashing system. DMF filtered water can be supplied to the backwash water tank, or cartridge filter effluent also can be supplied. During the construction or commissioning stage, this kind of filtered water can be temporarily used for the backwash water. But if RO starts in service, brine is the main source of the backwash water. Brine discharged from ERD will be divided by 2 streams. One is coming to the backwash water tank. The other will be discharged to the outfall. In the upper line, there are one small valve. It controls the back pressure. The backwashing flow rate will be controlled by a set of control valve and flow meter in the backwashing line. It is a common system. This slide shows the backwashing system in Laci care. The difference between conventional system and that of Laci care system is the bypassing pipe of backwashing tank. The pressure of the ELD discharge is 1.8 bar, and the pressure of backwashing pump discharge is 1.1 bar. The pressure difference between 2 points is 0.7 bar. If we reduce or maintain the pressure losses between 2 points, then we can remove backwash water tank or backwash water pump. This is our main concept of this task. This slide shows the DMF backwashing sequence in Laci care. When DMF starts backwash, one filter will be isolated from the DMF system. Water level will go down to backwash water level, which is 15 centimeters above top of answer site. At first, air scoring will be coming for 3 minutes. After that, concurrent flow. Air scoring plus low backwash water will coming for 2 minutes. The main backwashing process is the high flow rate backwash with 43.4 meters per hour of backwashing velocity and 6.5 minutes. When they complete the backwash, feed water will come and the rinse will start for 34 minutes. Backwash test was conducted without backwash pump operation in Laci care. The main criteria of the back pressure is 1.8 bar. If the back pressure is greater than 1.8 bar, then it will be negative impact on the feed pressure of RO membrane. So within the range, we want to know the maximum backwashing flow rate. By the test, we got the maximum backwashing velocity is 20.1 meters per hour. And during the test, we found 3 challenges. The first is the vibration of the piping and valves. So we cannot get enough backwashing flow. Second is the small diameter of bypassing pipe. The last one is existing backwash pump. It is the main barrier of the test. We cannot increase backwash flow because existing backwash pump. This slide shows the test of this backwashing. Upper 2 graph shows the profile of backwash flow rate. The left side figure is the previous backwashing condition. The right side is modified backwashing condition. We keep the same conditions of air scoring and concurrent flow, but we just reduce the high flow velocity backwash to 20 meters per hour from 43.4 meters per hour. but we increase duration of backwash to 13.3 minutes from 6.5 minutes. After completion of backwash, we visited DMF filter inside, and we checked the visual inspection. In your photo, you can find some red color. It is a residual ferric after backwash. By modification of the backwashing scheme, we can make filter more cleaner than before. This slide shows the innovative design of backwashing system. There are three big differences compared to conventional type backwashing system. First, we removed backwash water tank. Second, we install backwash water pump for standby usage only, not for duty. The last one is the flow control. Control valve on the discharge line will control the flow rate of the backwash using flow meter. When you apply this scheme to the new plant, then we can simplify the backwashing line, but it will work same function and high efficiency. This is a benefit of the test in the Laci care. We can save the capex of backwash water tank and backwash water pumps. And also, energy consumption can be saved. In Laci care, there are 2 backwash water tanks. Each tank has 2,800 cubic meter of volume. We can remove these 2 tanks. And also, there are 4 backwash pumps. Each pump has 9,770 cubic meter per hour of capacity. We can remove 2 pumps. You can find in the photo, this pump is very huge. By the modification, we can save energy consumption 848 megawatt hour per year, and we can reduce lots of number of valves and pipe lengths, and we can get flexible operation. This scheme will be implemented to the Jeddah 3 plant also. That's all. Thank you for your attention.
Thank you, Dr. Park, for this presentation. So the floor is open for questions. Do we have any questions here? So, okay, then I will give you one question. Okay, did you consider in the energy saving, which you mentioned at the end of the presentation, that at the end you're using a pressure on the brine? I think it was 1.8 bar. So did you include that in your energy calculation? So basically, you're not saving the energy from the pump because you're using a back pressure on the brine. Usually in different energy recovery systems, the brine outlet will have a much lower pressure. So this 1.8 bar is also energy which you're using. Is this included in your calculation?
Sorry.
You said in the last statement the energy saving because of yes. The pumps. And I'm saying there is an energy saving, yes, but on the other hand, you're using energy because the brine has still 1.8 bars. So you're not using this 1.8 bars. Usually it will be 0.2, 0.1 bar only, the brine. So there is already additional energy which you're using.
Yes, it depends on the site condition, but in case of Asaka and Zeta 3 plant, they have enough pressure on the ERD discharge. And also, Yanbu plant also have enough pressure. Until now, they waste energy. So by modification of the piping or valve operation, we can save and we can minimize the loss of energy.
Any questions from the audience? Here's one on the left side.
Hi, thank you for your presentation. I'm Fadi Saleh from Matito. One question, have you studied the effect of the high salinity backwash waste on the wastewater treatment system in the plant?
No, but in our test, we intend to use same volume of the wastewater. We keep the same conditions of air scoring and concurrent flow. We just modify the backwash velocity and duration. But total used volume of brine will be same as before.
The question was really on the salinity of the brine. Instead of that, we normally backwash with raw seawater. Are the wastewater treatment plant designed to handle high salinity waste? The equipment, for example, the clarifiers, the centrifuge, the backwash recovery system, let's say, or wastewater treatment system?
We did not compare the filtered water backwash and brine backwash, but within same condition, we just change the operating condition only. But we can achieve better performance of backwash.
Thank you.
Any other question on the end of the hall? Can you please bring a microphone there? Thanks.
My name is Mohammed Al-Masmoum from Jeddah plant. Actually, I have two questions. First one, your modification will be increase the backwash duration from 6.5 minutes to 13.3. During the SDI is high, did you think your modification will affect the quality of the water during the time of the when the SDI is high? Second question, did you add the vibration sensor on the turbocharger to check the vibration online? Thank you.
Unfortunately, we tested only short time for this test, but if we remove the backwash pump, then we can provide more backwash range. So even though high SDI condition, we can achieve high backwashing flow rate, I guess.
Okay, final question, please. Here on the right side.
My name is Abdel Nasser Mabrouk from Qatar Environment Research Institute. Thank you very much, Dr. Barker, for exciting project and really some real contribution. I have a follow-up question about energy efficiency. Now, I know you have boundary 1.8 bar outlet from ERD. Can you control, I mean, is it possible to control ERD, I mean, energy recovery system to make the outlet lower than 1.8, maybe so that no need to make any modification, and this 1 point. not clear. My voice not clear.
It's difficult to understand
Oh,
your question. Sorry.
I make it more clear. Your point that you make saving in energy because the ERD outlet is forced or is 1.8 bar, right?
Yes.
Is it possible to control ERD itself to reduce the outlet pressure so that maybe no need to make modification? This one point. I have another comment if just to answer this one.
When we design the plant, design engineer have to decide the discharge pressure of the ERD. But usually, plant needs some pressure to discharge continuously to the outfall. So at least they keep 1 bar or 1 point something bar as a design requirement. So if you decide the discharge pressure is lower than 1 bar or 0.5 bar, then this concept cannot be applied. But for the stable operation in plant, they decide a little bit higher pressure discharge.
Okay, the second concern, can you elaborate more how the residence time improve the quality of our cleaning process?
Sorry, one more time.
Again, the second point, you're finding that you're controlling residence time, right? Increase residence time.
Yes.
Because you remove the backwash tank, right?
No, no.
Oh, again, can you explain this? Because I didn't get your point.
Oh, okay. We want to keep the same, we want to use same volume of backwash water. Using same volume of backwash water, we just change the backwashing condition only. If we change the condition, backwashing condition, then we can make filter clearer than before. We just found if we connect directly from discharge of ERD to DMF, then we can backwash by existing pressure of discharge of ERD. We don't want to remove backwash. It was finding, not the purpose.
Okay. Thank you very much, Dr. Park, for this nice presentation. I hand over to...
Okay. We move to the last paper in the morning session. The paper is the UF-FOMD hybrid system for resources recycled from wastewater using SWRO brine as FO draw solution. Will be presented by Dr. Sheng Li. Sheng Li is a PhD, graduated from Delft University of Technology in Holland, and specialized in membrane management and sanitary engineering. He has more than 15 years innovation research experience in membrane-based water treatment, specialized in the membrane fouling area. Dr. Li, before he joined the SWCC, he's an associate professor in Chinese Academy of Science. He's now a senior expert at DTRI, SWEG. Please welcome Dr. Li to the floor.
Thank you, Chairman, for the kind introduction. Good morning, ladies and gentlemen. I'm Sheng Li. Today I will share with you concept proving study on the membrane technology base for resource recovery from the water desalination. So the UF-FOMD hybrid system was developed for the resource recovered from the wastewater desalination initially, but because of the, due to the high salinity requirement for the jaw solution in FO unit, the SWRO brine would be a good option to act as the jaw solution in this system, especially for the SWCC brine mining process generated brine, which has mainly the monovalent ions in the brine solution. So in the coming presentation, I'm going to cover more in details about this system. So let's start with the water demand in the Saudi Arabia. There are three main water consumption sectors in Saudi Arabia. It's mainly the agriculture sector, which covers 83% of the annual water consumption, and then followed by the urban usage and industrial consumption, which cover 13% and 4% respectively. And the kingdom overall water demand stands at an estimated 25.3 billion cubic meter per year. And according to the projection, it will slightly goes up to about 25.8 billion cubic per year to 2025. And where are these water from? It's mainly from the desalinated water and also the groundwater. So here we are mainly focusing on the consumption of the urban usage and also the industrial usage. For the agriculture sector, it's also it's another story because for the agriculture sector, now they mainly use 90% of the water from the groundwater. Considering the urban usage in Saudi Arabia, at the moment, according to data to 2019, about 35% of the water are coming from the fossil aquifer, which is deep in the rocks and non-renewable. If we extract it too much, then it would be difficult to take the water out from the aquifer again. And the remaining 65% is covered by the desalination technology. That's status of the water supply for the kingdom, but with the expansion, because of the population expansion, you can expect that the water consumption in the domestic sector, according to the survey of the people consumption or daily, it's about 263 liters per capita. And considering the population of Saudi Arabia is about 8 million cubic meter per day at the moment. And because of the expansion, the population, it will go up to 12.3 million cubic per day by 2040. And because of the 23rd vision, there will be industrial expansion in the kingdom as well. Besides the traditional oil refinery industry, the kingdom is also pushing forward the mineral and metal processing industry, automotive manufacturing in the kingdom, and also the farmer and biotechnology industry in the kingdom. And all these industry, they will need fresh water during their processing on manufacturing. It will be covered for the cooling, boiler feed, washing and painting for the automotive, and the sterilized processing and cell culturing for the farmer and biotech processing. So all these industry, they need fresh water, low salinity water. How we can supply enough amount of the fresh water for this expansion? We have a potential solutions, which traditional one with the seawater desalination, and or we can try to use the desalination for the urban industrial wastewater. If compare these two kinds of desalination method, you have a benefit, of course, for the seawater desalination, which has an unlimited amount because we are next to the sea, and it's a huge amount for us to extract water from it. But the seawater has high salinity, so it consumes a high energy input for the desalinated seawater. With the wastewater desalination, because of relative low salinity, we can use less energy, and the feed will be stable because it's coming routine processing of the industry. But for the seawater, depending on the seasonal variation, you have a different feed quality coming into in the plant. Especially during the algae bloom season, you have a lot of SWRO plant, they have the problem of a fouling issue. So how I would introduce an example for the using the UF-FOMD process for in the herbal medicine wastewater treatment for harvesting different resource inside of the wastewater. Here, the TCM stands for traditional Chinese medicine. It's a kind of herbal medicine manufacturing. In this wastewater, you can expect the macromolecule substances like the protein, polysaccharides, and also bioactive compounds, which molecular between, it's around 1,000 molecular Dalton. And then in there, of course, we have the water as a resource to recover. Going through this process, we are using the UF to remove the macromolecular waste substances out from wastewater, which is the protein and polysaccharides. For the later on downstream extraction, especially for polysaccharides, which potentially can be used for chemical raw material. And for the bioactive compounds, because here we are treating the herbal medicine wastewater, those bioactive compounds which are can be good for use as a livestock cultivation to prevent the disease in the livestock raising. And the purified water we will use it back into the processing of the medical production. So at the beginning, actually, we were trying to use the hybrid of UF and MD system, which has been shown that it's can reach our target to separate effectively the three components, macromolecular substances and bioactive compounds with 1,000 Dalton and also the pure water. But with this configuration, the UF-MD configuration, we have the problem of wetting issue. Because inside of the wastewater, there are some natural surfactant in the wastewater which can reduce hydrophobicity of the MD membranes. And then the contaminants can permeate through the hydrophobic MD membrane and then entering the condensate of the MD process. So because of this, we modified the process. We put an FO in between the UF and MD. We use the FO process to concentrate the bioactive compounds, and then we use a draw solution, just salt inside of the MD process, in the FO process, and the diluted draw solution we will recover in the MD process. In this configuration, the benefit is that we don't have the natural surfactant inside of MD and FO loop. So we can prevent the wetting issue in the MD process. So let's look at the results. How we do the experiment. First of all, we do with the real wastewater, the real TCM wastewater from the herbal tea production. And then after the UF pre-treatment, it will go into the FO. In the FO, we are using the 2 mole per liter NaCl solution. And the treated, extracted solution from the FO will be used at the feed of the MD. Here is what we are talking about for using the SWRO brine as a draw solution. For those participate the pre-conference workshop yesterday, you know, in SWCC we are implementing the sodium chloride and bromine production train in the plants. So in this configuration, part of the Seawater Ro brine will be used for the production of sodium chloride and bromine, and of course there's some concentrate Seawater Ro brine will be out for. For this one, it's mainly containing monovalent ions, mainly NaCl, so we can use it in here as the jaw solution of the FO system. After the evaluation of the effectiveness of the process, we are using also the synthetic water to further evaluate the removal of natural surfactant from, by the FO process, and then the effectiveness of preventing the wetting issue in the MD. Here's a setup. We use a fully automated lab-scale setup for the UF system, so it's enabled to, after a certain time in operation, we can do the backwashing with the system. The membrane we use is a 10,000 Dalton PES membrane operated at cross-flow mode. And the flux for the UF filtration is 60 LMH and operating at 1 bar. And for the FO and MD, you also use an automatic system that we can recycle the liquid on both sides of the membranes to extract. For FO process, we extract the water from the wastewater by the high salinity of sodium chloride solution. And for the MD process, we use the PVDF membrane operated at direct contact membrane distillation mode, and all of them are flowing in a counter current mode and with a cross flow velocity of 8.5 centimeters per second. And for the MD, the hot side is about 55 degrees Celsius. And because of the relative low temperature of MD process, we can consider use the waste heat of the plant. For example, for the medicine production, the TCM production, they have the herbal tea was boiled in front of the treatment scheme, so they have the waste heat to recycle to be used in the MD process. For the other oil refinery industry, there might be possibility for the reuse of the waste heat as well. So let's come to the results. Let's take a look at the effectiveness of the whole scheme in terms of generating water. You can see it here with the raw seawater. We have about 120 milligram per liter of TOC, and also a high concentration of total phosphate. By the pre-treatment of UF, it doesn't remove that much. Maximum we can remove 30% of the organic carbon out from the water. But when we reach the FO process, we can remove almost all of them, the contaminants from the wastewater, and generate a relative, quite high quality of the extracted, diluted FO jaw solution for the downstream MD process. And with the final polishing of the MD process, you can see that we have a quite good quality of the water for this use. And in terms of the UF performance, because of the high concentration of the organic carbon in the water, so there will be a fouling issue during the operation. But with the backwashing, after half an hour, we backwash with the perme for 1 minute at double flux. We can manage to maintain the permeability of the UF membranes. And here is a concentration of ammonium glycyrrhizinate. Actually, the ammonium glycyrrhizinate, that is the compounds we found in the medical wastewater, which are the natural existing surfactant and can deteriorate the performance of the MD system. That's why we take it out as a separate parameter to see how we can remove them in the FO system and prevent the wetting issue in the MD system. As you can see here, the ammonium glycinate in the raw seawater, raw water is a 1.1 milligram per liter. After the pretreatment, we didn't really remove that much of the substances by UF membranes. And then by FO, we can achieve a good rejection of these substances, and the concentration of the concentrated solution is also corresponding to the concentration factor of the FO fit solution after the process. You can see it here. The FO fit, we can reduce the volume of the reduction factor 2.3, and the concentration factor of increase of the ammonium glycinate is about 2.1. So we can really effectively remove the natural surfactant from the water by the FO process. We also double confirm with synthetic water with ammonium glycinate with the source only, and also run in the system to see how good we can remove these target substances to prevent the wetting issue in the MD process. And as you can see here, we also remove almost all of the ammonium glycinate from the water. And of course, because now the FO membranes are taking the main burden of removing the contaminants, we do observe a lot of fouling issue happening in the FO process. But as you can see here, the flux of each cycle is keep decreasing, and also we observe a kind of a cake layer formation on the FO membranes. And besides that, besides the flux decline, we also observe a kind of permeation, enhanced permeation of ammonium form nitrogen pass through the membrane because of it, most likely because of the concentration bipolarization buildup due to the fouling layer formation of FO membranes. But the good part of the FO membrane technology is that it's a no pressure driven process. So the fouling layer formed on the FO membranes are relatively easy to remove. By incorporating the air-water mixed scouring, we are successfully eliminate the fouling layer from the FO membranes. And comes back to the MD part, because we have removed all the natural surfactant from the wastewater by FO process, and then we check whether we really can solve the wetting issue in the MD process. As you can see here, the figure on the left-hand side, that is the blank. What the blank means that we use the clean water, molecule water, to run it in MD process and see how it performs as a base control. And then we use the UFMD configuration, the water treated by this configuration, and see how it performs in the MD system. And then as a comparison is the UFFOMD. That's the membranes after the process, and we take out the MD membrane and see how the contact angle and what is the hydrophobicity of these MD membranes after process. As you can see here, with the UFFOMD configuration, we have a contact angle, which means the hydrophobicity, which are quite close to the blank control. But with the one UFMD configuration, which have the elimination of natural surfactant by the FO process, the hydrophobicity of the MD membranes decrease dramatically, and we do observe that the water deterioration, water quality deterioration in the UFMD configuration as well. So summary, With the UFFO-MD process, we can separate the macromolecular substances, for example, polysaccharides, bioactive compounds, and water in the medical wastewater. And with the FO process, we can reject the natural surfactant and can concentrate somehow for this bioactive components, which can be used for some other applications. And the wetting issue of the MD, because of the existence of FO process, it can be eliminated as well. So, and in general, the wastewater desalination and purification could be an option or alternative source for increase the water supply in Saudi Arabia. So with that, that's all my presentation. Thank you for your attention.
Thank you, Dr. Lee, for a nice presentation. We have some time for questions. Do you have any questions? I'll start the question.
Yeah.
I think it's using FO to remove this surfactant to prevent membrane wetting is a great idea. Do you also observe any biofouling? Because this one is, you also have a membrane distillation and you have a high temperature, so I don't know, you run experiments long enough to observe the biofouling?
Yeah, for the process, we run about 10 to 15 days for the FO process. Within this period, we do observe fouling. The fouling is composed of organic substances, of course, with also some bacteria, microorganisms in there. But with the air scouring, we can maintain the permeability of FO membranes. But if we are talking about even longer term operation, months, that's something that need to be to run in pilot scale and see how it perform. I do agree with you that might be an issue for long-term operation, and that's also the next step. I would like to continue to see what we can come up with a solution if the biofouling is an issue.
Thank you. Yeah. Any other question? Yes, gentleman over there, the center.
Thank you for. Okay, thank you for your nice, innovative process and presentation. I just have first, what are the challenges when you are trying to scale up this process? Because you know this FO, MD, and prefabrication membranes are all not. There is no commercial models for this one. So what other concerns you have in scaling up?
Yep. For FO now. There are some projects and plants actually in operation in China. But it's not very high capacity. But we're talking about 1,000 cube per day. That's the scale of the FO process. And regarding the MD, yes, I haven't have too much details about the commercial scale of the MD process. Regarding the MD process, yes, for scaling up, first of all, the heat transfer coefficient, because the flux of the MD in terms of lab scale and large commercial scale, the efficiency would be one of the consideration. And there's another one, it's about the wetting issue, which we're trying to address it in the study, because especially when we work with the industrial wastewater, there are a lot of unexpected components in there, which might wet your membrane, MD membranes, and then make it not effective or to extract, to remove isolate the water from the liquid. So that would be the challenges that.
How about the perforation membranes? Have you considered replacing the MD membranes with the perforation membranes? Because you know Prefabrication membranes are hydrophilic, so I think the wetting issue will not be there effective. But I'm not sure how you thought about this or not.
Yep, you're right about this. The reason MD was selected is because the quality of the production is high. That was the reason. It really depends on the industrial reuse purpose. If you need a high purity or high quality of water to reuse, then that's also the reason we consider to use MD at the beginning, because it was back to the medical production train. But if the reuse purpose is not so high, you're right that it might be better to use reverse osmosis to recover the water.
I mean perforation membranes, not reverse osmosis. There is another type similar to MD membranes. It's called prefabrication membranes, which have been used in petrochemical industries and other applications. Have you any idea about it? Prefabrication membranes. Prefabrication membranes. It's exactly the same concept as MD membrane, except they are hydrophilic, and MD is hydrophobic.
Yeah.
So it depends on the selectivity for each component you are going for.
Yeah, but we haven't tried that kind of membrane before yet. Yeah.
Okay.
And okay, gentlemen, the center.
Thank you for the presentation. My question is about the viability of membrane distillation. Membrane distillation has been around for a long time, and it hasn't seen really large commercial applications. FO, I think it has a very clear market now. It's good for the treatment of difficult waters. It's not competitive with RO from the capital cost or energy consumption aspect. But membrane distillation, I mean, it has been around for a long time, and it hasn't really seen large-scale applications. Of course, it's a thermal technology, and you know all thermal technologies are not competitive with membrane technologies. And so I have always had doubts about the future of membrane distillation. So what do you think about this aspect of membrane distillation?
Yeah, thank you, Dr. Paso, for the question. Yes, I agree with you that until now, I don't see a large scale or big scale of MD process in operation. And for the MD, I think there is a possibility in the niche market. That's why, for example, like this process, when we're talking about the TCM wastewater, they have a high requirement of the water quality to generate it, and also they have the waste heat produced already inside of the plant. Then make MD process could be a possible or maybe beneficial option for this plant. But it really depends on the application. In some other application, in some other market, at the moment, and yeah, MD might not be a good option to continue. Yeah, it has to find a customized system. You have to go into the details of the original production plan, industrial plan, and what's their need, and then couple with the different membrane technology. So there might be a niche market for the MD, but then we need to go into the details of the existing production chain and see.
Okay. For your information, in the afternoon, I have a presentation about scaling of a membrane distillation. Perhaps that's better time we talk about this scaling of issues.
Okay, thank you.
Any other question? If you don't, I'll just close this presentation. Thank you again, Dr. Lee, for your nice presentation.
Thank you very much.
Okay. We'll have a lunch break. Yeah.
Thank you so much to wonderful chair and panelists this morning. As foreshadowed just now, we are about to break for lunch. We will resume back in here at 1 p.m. The lunch will take place on the other side of the corridor where we had coffee this morning. I would invite you back here for a very interesting session at 1 o'clock on the topic of innovation in membrane technology. Also running in parallel to that will be a workshop, also on the first floor, and the theme for that will be innovation in desalination to reduce environmental impact. So please enjoy your lunch. Thank you, ladies and gentlemen.
since the year 2000 has been focused on membrane-based seawater desalination technologies, such as RO, membrane distillation, and pressure-retarded osmosis. And his work has been documented in many scientific and engineering journals. He's published more than 100 research papers and 200 conference proceedings, papers, and abstracts. He's also acquired more than 10 patents and organized the Korea Desalination Society, KDS, back in 2011 and served as a founding president. Professor Kim?
Thank you. Thank you for the kind introduction. My topic today is scale-up of membrane distillation for seawater application. I have been involved in a couple of projects for this subject, so I'm going to share the experience I learned from this project. And you find many names down here. It's because this project, many people got involved, so I just list a few names to recognize their contributions. I'll start the presentation with some background information of membrane distillation, then move on to the scale-up of membrane distillation, and after that, I'll show you a few cases where this technology can be very useful, and then I'll end the presentation. So what is membrane distillation? Membrane distillation is a membrane process driven by vapor pressure difference. You have a membrane here, and this membrane separates two solutions, and you provide a vapor pressure difference between these two solutions. Then vapor moves from the higher pressure side to low pressure side through the membrane pores. That is membrane distillation. And this one is, how this one is different from typical water treatment membrane process? Two things. First one is membranes. We use hydrophobic membrane in membrane distillation, hydrophilic membrane in water treatment. And secondly, driving force. Vapor pressure difference is a driving force in membrane distillation. Water treatment, hydraulic pressure difference. You apply hydraulic pressure and push feed water toward membrane so that you can push water through membrane pores, leaving everything behind. That is water treatment membrane process. Because of that, they expect more fouling and less fouling in membrane distillation. And if you compare this one to the thermal process for seawater application, we can make a plant more compact and light for this membrane distillation. That is main advantage of this technology. It also has some downsides. First one is a vapor pressure difference. How we provide the vapor pressure difference? This is through temperature difference. So you increase the feed water temperature, then this feed water has a higher vapor pressure. Then vapor moves through the membrane pores. Also, we need to worry about membrane wetting. Water treatment, membrane wetted. But in membrane distillation, once membrane wetted, you cannot use it for membrane distillation because membrane distillation is not water, but vapor moves through the membrane pores. This membrane distillation is an interesting subject because it both involves simultaneous heat and mass transfer. Many people work on this subject, but very limited information of scale-up. So that's the reason we started this study. Why membrane distillation? Well, you all seawater desalination expert. You take seawater, desalinate, you produce fresh water. But in the course, you also have a brines. And we believe this membrane distillation is good for brine treatment. Well, so that discharging these brines back to the ocean is kind of waste. If you look at these figures, this figure is yesterday is shown by Nikolai. Actually, this one is prepared by UTS people. What this figure shows is minerals, resources contained in seawater. They divide these minerals into two groups. First one is economically feasible group. The other one is economically challenging group. They're divided by this line. And this one is based on concentration and price value. So that higher the price, And higher the concentration, these resource minerals becomes more attractive in terms of resource recovery. And that's what exactly we do in seawater desalination. You concentrate through the desalination. So that discharging these concentrated resources back to the ocean is kind of waste. So we put the membrane distillation for further concentration, taking brines from desalination and further squeeze so that we can produce more fresh water, also more concentrate, so they put these minerals in a better position for resource recovery. And we work on over a couple of research projects this topic. First one, we started 2013. We call this research group Membrane Distillation. A main mission of this project is to design and fabricate membrane distillation, pressure retard osmosis, and lithium recovery. And this first project ended 2018. 2018, we started a new project, phase 2 project. This one we call MD+, and this is this one is focused on membrane distillation, especially operations. Has some target values like performance ratio, specific energy consumption, and operational durations. Okay? Now scale up membrane distillation. If you just look at the definition, scale up. What is scale up? Scale up is to increase something in size, amount, or production, or just increase according to a fixed ratio. These are dictionary definition of scale up. Basically what it says is size increase. But it turns out scale up is much more complicated. It's not that simple, much more complicated. In the right-hand side, you find a figure. What this figure shows is actually it compares two module performances, more fluxes actually. And two different manufacturers, they fabricated full-scale modules, and they send us, and we evaluate their performances. The blue one is a lab-scale module, fluxes, and red one is full-scale module fluxes. So you can tell the difference in fluxes between lab-scale and full-scale module. So depending on how you make it, full-scale module performance can be very much different, so that this scale-up is not that simple. So scale-up is basically building a plant. You develop a full-scale module, and using this full-scale module, you build a plant. So I'll just explain how we develop the full-scale module, then build a plant. And this slide shows factors you need to consider when you develop full-scale membrane and modules. Like you have to decide whether you go with hollow fiber or flat sheet. Also decide the membrane material, properties, and membrane area, how many membranes are put into single module, fiber length, and other things. Well, flat sheet, hollow fiber, it has its own pros and cons. Flat sheet is has an advantage in terms of heat supply and recovery, but hollow fiber has an advantage in packing density. So we decided to go with the hollow fiber. And this slide, it shows the membrane properties affect mass transfer and heat transfer. So when you develop membrane, you need to consider these factors, properties, and optimize. And this slide, it compares polymers, four hydrophobic polymers, in terms of price and mass production easiness and strong oxidant resistance. So you need to also consider these things. And Econity is a Korean hollow fiber membrane manufacturer. They work together with us to develop the full-scale membrane distillation membrane and modules. They decided to go with the polyethylene and PVDF. And this slide, it shows the properties of these PVDF and PE fibers they developed for membrane distillation applications. Basically, these two fibers, they have the same properties, average pore size and porosity and contact angle only different in thickness. PVDF thicker than polyethylene. So with these membranes, they developed the full-scale module. Actually, they developed the two modules. First module is for vacuum membrane distillation applications. And second module, you can use for VMD and direct contact membrane distillation. And this picture, it shows VMD application modules. It is, the module material is, I don't think you can follow this one, it's too small, but the module material is ABS, and potting material is polyurethane, both are heat-resistant materials, and membrane area 10 meters square, and fiber length is 450 millimeter, and the maximum operating temperature is recommended 80 degrees. So with this full-scale module, we build a plan, considering this configuration and energy recovery and things. And this slide is show the typical membrane distillation configuration, direct contact membrane distillation, hot feed water and cold condensate, direct contact with the membrane. Air gap, you put air gap so that we reduce heat loss, but you also decrease the fluxes. And sweeping gas, instead of using liquid, you use gas in the cold condensate. And vacuum, you apply vacuum at the cold condensate so that you can increase the fluxes. And we built 2 pilot plants using the, under this project, MD Plus project. We used hollow fiber module based on polyethylene membrane fibers, and the membrane area 10 meters square. Configuration is VMD, vacuum membrane distillation. We put the energy recovery device, TVC, thermal vapor recompressor. Build the 2 plants. First one is daily capacity is 4 meter cube. Second one is 8 meter cube. And they have, both plants have different purposes. Plant number 1 is to develop and secure operational technologies. We just put this one in Korea. We play with it to secure these operational technologies. And plan number 2, this is for the long-term operations. And this slide shows the study flow chart of piloting. First, starting with a basic design, detailed design, fabricate the plant at the shop, and simultaneously you prepare the site, pilot plant site, transport, install, and then also test the module, and then start the operations. And this one show the picture. Left side show the pilot plant with we manufacture, fabricated over 2 racks. You can see the 2 modules, and this one put into 40-feet container and transported the piloting site, which is southeast corner of Korea. So this is port city, so we have an access to seawater. And the right side, I show the final piloting pictures. We put 4 containers. Container 1 is MD pilot plant. Container 2 is, number 2 is pre-treatment. Container number 3, office container. Container number 4 is utility containers. And this one shows the site preparation, utility connection, permit. Probably you know better than me. We're starting with this one, is connecting utilities. It takes about 1.5 years, starting from 2019. In 2020 summer is ready to operate, so we start the operation from 2020 summer. And this one shows the module tester. We make a module testers. So once a manufacturer sends us the modules, on site we test the module performance, mainly production, flux, and electric conductivity of permeate. Once we're happy, we just plug into the plant. And we also make a short video, short films, explaining, introducing this pilot plant. And this is a link, YouTube link. Through this link, you can get more information. So we do operate it the plant. And I'm going to show you some operation data. It's like operation data, and also fouling, cleaning, and wetting. This is operation data starting from 2020 summer and 2020 this year's spring. So you can see blue line is production, red line is PR. So you can see this one actually fluctuate. This is because we change the operation conditions. Like sometimes we operate a pilot plant with TVC on, sometimes TVC off. And also we operate this plant with two modules, sometimes 3 modules, and different batches of modules. We also vary the operating parameters like vacuum pressure, energy input, and circulation flow rate. And this one shows the water quality. Typical, the red one is seawater, pH 7.7, TDS at 35,000 milligram per liter. And right side, MD permeate, this TDS is about 2 milligram per liter. So it's about, in terms of ion rejection, it's 4 log rejection. So it's a typical result you expect from these MDs. And in the middle, you find the sand filter and microfilters. These are pre-treatment water quality. Actually, this seawater was highly contaminated by the particles. You can see turbidity is 20, SS suspended solid is 34 milligram per liter. Initially, we put small sand filter, but it was not good enough to take out particles, so we put the microfilters. And this slide, it just kind of summary our operations. It compares design stage expectation and operational results. At the design stage, when we operate this pilot plant with a vacuum pressure of 0.15 bar, temperature is 75 degrees, then we expect the production of a 4.2 meter cube daily production. Then flux is 8.8 LMH, PR is 1.75, SEC is 2.1 kilowatt hour per meter cube. And our actual operation, similar condition to the design stage, we got higher production, 4.7 meter cube per day, and but flux was lower because of this the module difference. Design stage, we expected 2 modules, but the module performance was not good enough, so that we put 1 more module. So 3 modules, the production increased, flux decreased, and PR was slightly lower than expectation. PR is related to TVC. TVC performance was not good enough, so that because of that, we have a slightly lower PR. SEC 2.07. And this SEC, you're very familiar with this. SEC is very much dependent on the pump efficiency. But this is small plant. If you have a large plant, you can decrease these SEC values. And I'll show you some fouling data. Okay, membrane distillation. Everybody talking about foulings, and do we actually observe fouling actually occurs? Yeah, fouling occurred. We observed foulings because of a poor pretreatment and module defection, also during the operations. And this left side is because of poor pretreatment. It looks like I have short of time, so I'm going to, we observed the foulings. We did the autopsies. And the autopsy result, this one showed the autopsy result. In summary, what we found is calcium carbonate. Then, what we did is we developed the cleanings. The next question is, can we clean this fouled membrane? Can you recover this performance? I didn't put the result here because we don't have kind of inconsistent results. But our preliminary result says we can clean fouled membrane, but not 100%. How about wetting? Yeah, membrane wetting. We observed the membrane wetting. This one, we saw, you can tell the LEP, liquid entry pressure, and contact angle. The fouled membrane's LEP and contact angle is half of the virgin values. And go back to pilot plant number 2. It's going to operate here in this Red Sea area. up north from Jeddah, plant, together with SWCC, and is going to put there and take the RO brine and operate there for 6 months to check this operational sustainability. And this one shows the 3D drawing of a pilot plant. This one is actually already in Jeddah port. And I show you 3 cases of membrane distillation, very useful. We apply this one to treat hot saline groundwater. Well, in certain part, there is groundwater, temperature high, salinity high. So what they do is they use RO, but because of high temperature, they put the cooling before upstream of RO. So instead of this cooling and RO, we use membrane distillation, in this case SGMD, because we suspect these cases usually groundwater located inland, difficult to find the seawater for cooling water. So this one shows the results. And also, this one is we use our team our team members use the membrane distillation to produce fertilizer from urine. Urine is very rich in nitrogen source. From this one, we use membrane distillation to produce fertilizers. And water harvesting from air using osmotic distillation and membrane distillation. Well, this is kind of 2-stage process. Using the osmotic distillation, you suck up water from air. Using membrane distillation, you release this water so that you can produce fresh water from airs. What is osmotic distillation? This one is similar to membrane distillation. Same vapor pressure differences are driving force. But in this case, not temperature difference, but concentration difference, so that you don't need any energy inputs. So with this combination, we can, we run this test. This one works very well. Well, scale up as possible. We can scale up membrane distillation. What is most important thing? The module optimization is the most important thing. And membrane fouling, yes, membrane fouled. So that we need to optimize the cleaning procedures, and also we need to pre-treatment. Membrane also wetted, so we need to develop the de-wetting method. And membrane distillation can be very useful, not just for seawater application, it can be used for many other areas. Thank you, thank you. Sorry.
Thank you, Professor Kim. Any questions about membrane distillation scaling from the audience? There's one question over there. Please state your name and affiliation.
عبد الناصر أبو خليوة حمد بن خليفة University قطر Qatar Energy Environment Research Institute. Thank you very much for very exciting and presentation and project. Actually, I have 2 questions, one in module level and one in process level. I mean, which you already touch both area. For module level, I mean for scale up the maximum membrane surface area. You employed already about 10 square meter surface area. I'm asking about is there any possibility to go further or beyond 10 square meter in terms of scale up, and what is the impact in the baking density on pressure drop in the module? This one, the first question. I have another question, but
okay.
Please, if you can focus on this.
Okay, actually, the equality, the manufacturers try to go higher membrane areas. We tried the higher membrane areas, 20 meters square, but the flux declined. So the production was same, so we decided to stop at 10 meters square. But so that's what I'm saying is you need the good membrane manufacturers. If you just optimize the membrane, the modules, I think we can go higher membrane areas. But with this, the manufacturer, that's the best we can go. So that's the reason we stop at 10 meters square.
Okay, thank you for this point. The second question relating the, I observed that the specific energy consumption you calculated is really very low. have you considered thermal energy beside pumping power, or this is just a pumping power?
This is just electricity.
Okay, so it's pumping power.
No thermal energy.
Okay, because I think it would be fair to consider thermal to compare with that one. Also, again, this PR, performance ratio, is still 1. I think, have you considered multi-effect vacuum membrane distillation to resolve this PR, or can reach up to 10, so that specific energy consumption could be increased?
Yeah, we consider. We did some preliminary calculations, actually. But this pilot, we just decided to go with the one stage. But yes, we did some calculations. And
what did you find?
Well, it depends. We can, my initial calculation with TBC on, I can increase the PR up to 5 point something. Without TBC, 2.8 something. It's 5-degree differences. So that if you just, if you lower the temperature difference, probably we have different results. But that's my calculations.
Thank you very much. Thank you.
Thank you, Professor Kim. Our next presentation is about chlorine-resistant anti-fouling TFC RO membranes with vacuum UV irradiation, presented by Professor Marwa Salabi. She's a full professor in Chemical Engineering Department in the National Research Center. Since 2020, member of the Flat Sheet Membrane and Spiral Wound Module Center at NRC. She's the main representative of the Egyptian Society for Membrane Technology and its application, which helps in the development of public awareness for membrane technology in water and in wastewater treatment. She has worked in the field of process development for different chemical engineering plants, and she's the application of optimized research in the field of RO brackets desalination units. Professor Shalabi has 53 international articles in nanomaterials fabrication, chemical treatment in wastewater, and membrane applications. Professor Shalabi.
Thank you for this nice presentation, Mr. Chair. First of all, good afternoon, all of you. I'd like to thank the organizing committee of IDA and SWCC for letting me have this presentation. As we said, that my title is the Chlorine Resistance Anti-Fouling TFC RO Membranes with Vacuum UV Irradiation. And this work is in a collaboration between the National Research Center in Egypt and Fraunhofer Institute for Coating Technology in Bremen, Germany. This is one of our international collaboration projects, which is an ongoing research. In my presentation today, I'll talk about a brief background of our situation in Egypt, and the problems for RO membranes, our suggested solutions, and experimental work results and some of our discussions, how we look for the large-scale applications and the lab-scale achievements, and finally the conclusions. If we are talking about Egypt, generally, first, worldwide, we have a water shortage problem that the concentration or the availability of the salt water counts over 97% of the worldwide water distribution. Here you can see the projection for 2025 water shortage problem. Many countries will have a scarcity in the orange and red colors. You can see the map here clear. So, if we talk especially for us in Egypt, maybe we are having some of the desalination sources, which only 0.6%, but the main water resource comes from the surface water, about 88%, and only 11% for the groundwater resource. This means that the per capita, and with the higher population of Egypt, which increases and increase, this means that we are getting to the water stress and getting after this to the water scarcity as being seen here, to reach 350, about 350 meter cube per capita by 2050. So the current situation is depending upon the desalination, depending upon RO. So our research institute and the governmental institutions in Egypt is now devoting their research to the development for RO membranes. Okay, development is a good or a key factor for many industries, but when we are talking about membranes, we have to talk about the recent problems. As we go to the desalination plants and the other factories and industrial areas in Egypt, we see that one of the most or the great problems which we deal with is the fouling and the chlorine resistance. As Egypt is one of the developing countries, so it's not easy to deal with using desalination and getting in many sectors while replacing and having the cost for replacing modules for RO with a narrow range of lifetime. So if we have a look here, you can see just a look for some types of the inorganic or the biofouling found for the sheets for the membrane. Also another view for some modules for showing these fouling. Another topic which is clear here for the current situation is the presence of the chlorine exposure problems, and this is mainly is supposed when we are talking with these membranes with the polyamide layer, which is a selective layer. Here we can find a photo for pristine polyamide membranes and the attack for the HOCl, which goes to the getting red or getting deterioration and breaking down for the polyamide layer. When we are talking about the presence of chlorine in exposure to the polyamide, we are talking about the group HOCl, which increases, makes this, the polyamide hydrolysis, makes such hydrolysis reaction, which is highly favored in the alkaline medium. And this means that the membrane will increase its permeability, sure, because the selective layer is going to deterioration, which will reflect upon the decrease in the percentage reduction. This one of our suggested solutions, chemical treatments. In my presentation today, I'll have a look for some chemical treatments. I put two types from our research for the chemical treatments for the RO membrane to withstand with the chlorine exposure and have a good anti-fouling behavior, and one physical treatment. So I'll have both of them today. The first one of the chemicals is the treatment of graphene oxide, and the chemistry of graphene oxide is one of the promising, excellent or promising techniques which is been changing the characteristics of the membranes. In this work, we are trying to highlight the effect of graphene oxide in addition to as a nanostructure with blended with three types of zinc oxide nanostructure with different morphologies in the sphere structure, in the rod structure, and in the flower structure. All of these were made by the sol gel method and blended with graphene oxide. In this work, we are trying to highlight the effect of the presence of these nanostructures in the interfacial polymerization layer, mainly in the aqueous phase layer accompanied with metaphenylene diamine. The effect here was clear to show that by blending different concentrations of zinc oxide with graphene by the different three morphologies which I have said, that the best one is the spherical structure of zinc, which is found to be 0.03% as by weight in graphene oxide to get a hydrophilic membrane of about a 50-degree contact angle, water contact angle. Sorry. This is the structure, the scanning electron microscope morphology for these TFC membranes. Here you can find the pristine membrane, the one in the left, the figure A and E. A is getting the top surface and E getting the cross-sectional cut for the membranes. You can see here in this figure the pristine one, and when we are going to 0.03, which is D and H, is the one here, the change in the morphology is clear, which reflects upon the enhancement in the properties and characteristics. Sorry. While comparing this study with others, we can find a great enhancement in the percentage rejection for the sodium chloride, which is reaching about 100% when compared to the other literature, which showing 98, 99, and 96, something in the same range. Also, the productivity of the zinc oxide spherical structure with graphene oxide was giving about 30 maximum productivity of 30 LMH. Here you can find the anti-fouling study, which is done by mixing humic acid with calcium chloride and sodium chloride. And after getting the compaction for the membrane by getting some filtration for the system for evaluating the membranes for almost 180 minutes with distilled water, you can find a change in the behavior between the pristine membrane and the zinc and the modified membrane using zinc oxide spherical structure with the others flowers and rod structures. You can see here the red ones also the best one, which having almost maybe a little bit of change for the foulant. Also here, a study for the chlorine exposure. After exposing the membranes using these nanostructures for graphene oxide and zinc oxide, you can see the upper one, which is A and B for the membranes before chlorination, and the bottom figures for the membranes after. And it's clear that the pristine membrane was highly affected, but the one treated with graphene oxide and zinc oxide nanospheres seems to be unaffected. The change here can be clear in the formation of the peak for the carbon oxygen, which show here to have only 2.2% intensity for the pristine membrane, while after getting chlorinated, it increases to reach about 17%. This means the complete change in the polyamide layer and the formation of new products or new structures. Completely different with the other side, which is giving graphene oxide, zinc oxide nanospheres, and showing that the same peak is not highly changed. It's about 12.9 and decreases to only 11.4. Okay. So we are getting now to highlight the effect of graphene oxide nanostructure, and it's not a new information or a new finding. All of us know that the graphene oxide have an excellent structure, but our addition today is to be embedded in the polymeric structure for the membranes or embedded in the polyamide layer, not having a graphene oxide membrane by its own. This means that this good chlorine-resistant suppression is getting to the graphene oxide presence. When we are looking about the fouling problem, we can also have such suggested strategy to put it away by getting the spacer geometry or the feed spacer found in the RO modules. It's one which is very important item which is highly responsible for controlling the fouling and the biofouling process. Okay. The other chemical treatment in our work today is the treatment of commercial thin film composite membranes, RO membranes, which is commercial ones, is treated by mixed PVA, polyvinyl alcohol, and zinc oxide nanospheres in the presence of glyceraldehyde as cross-linkers and some additives to stabilize the layer. Okay. In this work, we have compared between three membranes, MT31 and 32 and 33, where 33, which is the one having the percentage of zinc oxide nanospheres. Here you can find the change in the contact angle before and after chlorine exposure. We can find that M33, which is the one having the zinc, to be having, before the exposure, having about 10 degrees for the contact angle, showing a higher hydrophilicity, which increases to reach 49 after being exposed, which is the lowest number or the lowest angle when compared to the contact angle for the pristine one, which changed from 28 to 55. Okay. This is also a clear morphology or a clear scanning electron microscope giving the morphology change after exposure for the chlorine to show the effect of this deterioration caused by the chlorine exposure. The presence of the PVA layer over the polyamide layer shows a great enhancement in the percentage flux recovery ratio to reach about 59% for the flux recovery ratio when compared by increasing the percentage of reversible and irreversible, by decreasing the percentage of reversible and irreversible fouling. The last treatment, which is the physical one, which is used in the Fraunhofer Fraunhofer Institute for Coating Technology in the plasma and vacuum UV department in Germany. This work is done over the thin film composite membranes, where the membranes is being subjected to vacuum UV by using different pretreatments like ultrasonic, like the presence of some mercury lamps, like water cleaning. The change here in the irradiation was studied to show the effect of the different irradiations and their stability over membrane surface, to see that while for the reference membrane, which is untreated, the contact angle is the same. Okay. But for the ones which is treated by the irradiation, you can find here there is, after getting 4 days away from the radiation, the one which is having vacuum radiation with 1 meter per minute, having an increase in the radiation, which is not probably a good value. For the one which is having 10 meters per minute, increase also is found, but for the one which having 30 meters per minute, a decrease occurs. For these treatments, 1 meter per minute, we can find the contact angle to reach about 12 degrees, while for these, for 10 meters per minute, the increase in the contact angle adversely affects the hydrophilicity for these membranes. Also, this is some of the photos for the top layer for the polyamide TFC membranes, the one treated with the ultrasonic bath, having some defects for the polyamide layer. Also here, some
comparison between the XPS showing the percentage of the carbon, oxygen, and other elements for the membrane without and with water cleaning before irradiation. Here, the performance, membrane performance after having vacuum irradiation, it was found that if we look for the pristine membrane, the one in the violet color, here you can find that the pristine membrane and the membrane which is treated with the mercury lamp by the velocity 0.3 meter per minute, having the same percentage rejection as the membrane which is the pristine one. Thus, the rejection is not affected by the presence of this irradiation. While for the flux, also the flux tends to be the same for also the mercury treatment. The flux for the vacuum UV 0.3 meter per minute is higher, and this means that some deterioration is going to the membrane, and so the rejection is very low to reach about 20%. This means that the membrane seems to be destroyed, or the polyamide layer seems to be destroyed by these treatments. Also, the scanning electron microscope here can show the pristine membrane, the TFC layer, which is the familiar one, and as shown the vacuum UV, you can see here some deterioration in the layer. For the mercury 0.3, you can find that the top surface and the cross-section seems to not to be affected. Here, finally, I can have a look for our large-scale applications in our laboratories in Egypt. We have the large-scale RO membranes to be casted with the continuous membrane casting machine, and for the Spiral 1 modules, we have also our own rolling system, rolling and fiberglassing system. Also, we have here the pilot testing units for our modules or for our work, for our research work, not to be validated on the lab scale only, but to go to the pilot scale by using different membranes, 4021, 4040, and 8040 in some of our implemented desalination and wastewater treatment plants. Finally, our conclusions here. We are here to say that the exposure to chlorine highly affected the surface of the membranes, but in the presence of zinc nanostructures, this layer or the polyamide layer was highly enhanced. Also, the fouling behavior and the flux recovery ratio was the same. The treatment of the TFC membrane enhances the hydrophilicity to reach the minimum of 8.7 degrees. Especially at optimized vacuum UV or irradiation treatments. The minimum contact angle was achieved during the deposition of the presence of the zinc with the PVA tends to be 10 degrees. Ultrasound or ultrasonic baths deteriorate the polyamide layer. The best performance for the vacuum irradiation was done by the mercury vacuum UV lamp. Finally, I would like to invite you all to attend our third international conference for membrane technology and its application, which will be held in Cairo, in Triumph, Heliopolis, from 15 to 16 August. If so, please register on our website or contact us for any other informations. This is my acknowledgements to my research group for MTAIC and for the Egyptian Society for Membrane Technology and its application, and sure for our partners and in the projects from Fraunhofer IFAM in Bremen, Germany. Thank you.
Thank you, Professor Salabi. Certainly fouling is a problem that we find commonly in our desalination plants today. Any questions for Professor Salabi? Okay, I guess it was very clear. Thank you very much.
There's one question here.
I'm sorry. There's one question. Okay, sorry.
I'm here.
Sorry about that. I didn't see your.
That's okay. Thank you, Professor. Arjen Edelat, PWS. Can you tell me a little bit about your casting equipment in your lab?
Excuse me, can you raise your voice?
Yeah, can you tell us a little about your casting machine in your lab? What type of membranes do you cast, and you know, what sort of sizes?
Our casting machine in Cairo in our laboratory is a continuous phase casting machine. We are getting different sizes from this machine. We can get a size for about 1 meter in diameter, and getting too long length, we can reach to about 500 or certain 1,000s. But for our research facilities, we don't need this. So we are using this casting machine for getting modules which sizes, which having household one, which is about 30 centimeters in the width, and up to the one which is 50 centimeters for the 4021, and the others, which is the commercial ones, which having the, a width of 1 meter, which is the 4040, and also we have the 8040.
Great. So it's just casting or coating as well? How do you put your graphene on the surface of the membrane?
Yeah. For the large-scale applications, we are still have some missing equipments for getting the upscale coating, because this work is done for the small scale, because it needs some sophistications for the large-scale applications. Especially, we are a research center. We are not industry. We are not selling products. We are just validating our research. We are trying to go to the industrial entity or some which have problems to say that we have solved your problem in a large-scale applications.
Thank you.
You're welcome.
Okay, our next speaker is Mr. Takahito Nagao, who is a senior engineer in Membrane Business Development Department at Toyobo, where he leads the membrane products development for brine concentration. Since 2010, he was a research engineer in Membrane Development Group at Toyobo Corporation Research Center, and he has made many research contributions in membrane development as well as membrane performance analysis. He has a bachelor and master degree in agricultural science from Kyoto University. Today, he will present about development of membrane for osmotically assisted reverse osmosis and update for commercial project. Please welcome Mr. Nagao.
Okay, thank you for the kind introduction, Dr. Im. My name is Takahito Nagao from Toyobo, and today I will introduce the development of the membrane for osmotically assisted reverse osmosis, and I will update our commercial project. So today's outline is, firstly, I would like to introduce our newly developed membrane for the brine concentration, and then I will introduce some of the references in the industry cases. So the brine concentration market is large and fast-growing market, generating $1.8 billion opportunity for the next 5 years. By industrial segments, power, oil and gas, mining being the largest, and together representing 70% of the total market. So this is a broad technology landscape of the brine concentration technology mapped by the energy usage and total dissolved solids to be achieved. As you know, the energy is one of the critical issues of the brine concentration technology, as the energy increases dramatically with the concentration level to be achieved. Currently, some of the membrane-based brine concentration technology have been proposed, and these technologies are challenging to the conventional thermal brine concentration technology with the low energy consumption less than 20 kilowatt-hour per cubic meter. Compared to this membrane-based brine concentration technology, Toyobo's brine concentration technology is an innovative technology to enable you to concentrate brines more than 200,000 milligrams per liter with far less energy than the currently available technology and newly developed other brine concentration technology. So in terms of application, our brine concentration hollow fiber membrane technology can help you achieve the following. So firstly, we can reduce the capex and opex in thermal evaporator and crystallizer zero liquid discharge system. And also, we can minimize the volume of difficult to treat wastewaters. We can also deliver the high recovery for the desalination in the existing reverse osmosis plant. And also, we can increase the wastewater use rate for the various industries. And finally, we can also recover the variables from the brine and wastewater streams. So this is a simplified illustration of our brine concentration membrane module. It has a 4-port system, which is the inlet and outlet of the dilute solution, which we call bore side, and one for the concentrated solution, which we call shell side. And on the right-hand side are the specification of our membrane module, and I would like to highlight the membrane material is a chloride-intolerant material called cellulose trustate. And also, we have very large surface area of 600 square meters of one membrane module. And there are some feed water requirements, namely pH and temperature. And also, flux varies depending on the feed solution and final solution as shown in this table. So before going into the detail of the process, I would like to share the key advantages of Toyobo's brine concentration membrane leading the stable and effective and energy efficient brine concentration process. As the only supplier of the hollow fiber brine concentration membrane made by cellulose trustate, the advantages I will mention are so unique to our membrane technology. And advantages have been already appreciated by the customers having the success commercial project in some of the key industries. And as I mentioned, our brine concentration membrane technology can achieve the concentration level of 200,000 milligrams per liter with only using 7 megapascal pumping requirement. So it is a significantly energy-saving process and more energy efficient than the conventional reverse osmosis technology, which requires 10 megapascal only to achieve 120,000 milligrams per liter concentration. So thanks to the reduction in pumping requirement, we can offer the more than 70% energy saving compared to the typical thermal brine concentration process, and also more than 40% energy saving compared to the other membrane-based brine concentration technology like forward osmosis, membrane distillation, and others. And also, our chloride-intolerant membrane material lets you manage biofouling more easily with the direct chloride injection to the feed water without harming the membrane material. And also, other advantages include no need for draw solution like forward osmosis and high membrane surface area for efficient operations and reduced biofouling. And finally, the greater pressure resistance, which enables applications for the various industries. So, how does our technology work? The illustration shows the basic concept of the Toyobo's brine concentration technology compared to the conventional reverse osmosis technology. So our brine concentration process usually takes a brine from reverse osmosis process, but the concept is fundamentally different. So unlike reverse osmosis process, which takes a single solution across the membrane to generate the brine flow and permeate flow as well, we usually apply two solutions of similar or same salinity solutions across the membrane to generate the concentrated flow and dilute flow as well. So as you can see, this configuration can effectively minimize the osmotic pressure difference across the membrane, and therefore we can reduce the hydraulic pressure to make water permeation from one side to the other side. Also, our brine concentration process can be operated in stage configuration as shown in this here, and the concentration is sequentially increases the concentration level the customer requires. And as you can see, the portion of the product is recirculated back at each stages. It is for minimizing the osmotic pressure difference at each stages. And using this arrangement, we can concentrate feed solution more than 200,000 milligram per liter with only one high pressure pump for the RO feed. This is because our brine concentration process can be operated with the residual brine pressure from RO. So I'd like to introduce one example of the brine concentration application. In the current zero liquid discharge process, the seawater or feed water is concentrated by RO to around 70,000 milligram per liter, and then RO brine is applied to the thermal process to be concentrated to the saturated concentration. And then the saturated concentration solution is applied to the crystallizer to separate liquid from solid completely. So in this process, the permeate flow, in terms of the permeate capacity, we can obtain almost the same amount from RO and thermal as well. So brine concentration process can be applied to concentrate RO brine more and also reduce the thermal capacity. So when we put the brine concentration, multi-stage brine concentration process between the RO and thermal process, we can concentrate RO brine to around 200,000 milligram per liter, and then the amount of solution applied to the thermal process is highly reduced. And as I mentioned, our brine concentration process can generate the dilute flow from brine concentration membrane, and this diluted flow can be recycled as RO feed to get more permeate from RO. So in this process, we can obtain 2 times RO permeate compared to the current process, and also the required capacity in thermal process is 10 times smaller than the current process. Also, the theoretical power consumption is 3 times less than the current process, mainly due to the reduction in thermal capacity. So, the next, I would like to introduce references in brine concentration application. So this is references all over the world using our brine concentration membrane module. As you can see, most of our references in the East Asia and South Asia for the wastewater zero liquid discharge system, and it is due to the, especially in India and China, there are some very strict restriction in discharging wastewater stream to the environment. And also we have the some of the salt production references in Southeast Asia and East Asia also. And finally, we have the RO recovery increase and the brine mining references in the Middle East. So I will introduce some of these references in the next slide. The first reference is a pilot test using the actual RO brine stream. So pilot test was performed in the SWCC Jubail RO plant. And you can see in this picture, there is a white 20 feet container. So one Toyobo's brine concentration membrane and required equipment was installed in this white container. And the RO brine from Jubail RO plant was firstly stored in the white tank, and then the feed water was applied to our brine concentration membrane to both sides of the membrane to generate the concentrate stream and dilute stream as well. The pilot test was performed from September 2020 to March 2022 using the actual RO brine from the Jubail RO plant. And also we have confirmed the 8,000 hours, more than 8,000 hours, very stable operation without injecting the antiscalant before applying the solution to our brine concentration membrane module. And through this pilot test, we have also confirmed that our performance projection program matched very well with the actually obtained result using actual RO brine stream. So the next reference is the commercial OARO plant in Indonesia. So we are thinking this should be the first, world first commercial OAR plant. This is using the Hylex technology, and the plant contains ultrafiltration, non-filtration, Seawater Ro, and OARO, MVR crystallizer unit to make a solid salt from the seawater. And in this system, the 1,080 pieces of brine concentration membrane manufactured by Toyobo were used in OARO process. And in this plant, the daily water production is 27,000 cubic meter, and annual salt production was 220,000 tons as a food-grade salt. And the off-taker will be one of the major food manufacturers in Indonesia. And the plant is under construction, and we will start operation by the first quarter of the next year. And the location is Cilegon. You can see the map there. And Cilegon is a major coastal industrial city in Indonesia and located at the northwest side of the Java Island. So this is a specification of our commercial OARO plant. So I would like to highlight the overall recovery will be 78% based on the intake capacity, and also the specific power consumption will be 3.5 kilowatt-hour per cubic meter per feed solution. The right-hand side is the flow diagram of the commercial plant, and the intake capacity is 34,000 cubic meter per day, and we can get 27,000 cubic meter per day water production from RO membrane and MVR also. And also we can get 630 tons salt per day from the crystallizer. So this is a drawing of our commercial plant. So on the left side, we have the BOP, and right side, pre-treatment there, including the ultrafiltration, non-filtration, Seawater Ro, and we have the brine concentration unit in the middle, and then crystallizer here. The area is 60,000 square meter with a perimeter of 1,500 meter. Our length is 500 times 200 meter around. So this is a three-dimensional drawing of our commercial OARO plant. At the left side, we have the ultrafiltration unit, and next is the non-filtration unit. And in the middle, we have the Seawater Ro unit, and on the right, we have the OAR unit there. And after the OAR unit, we use the MVR crystallizer unit manufactured by GEA Messo in Germany. And this unit can convert the 3,700 cubic meter per day with 180,000 milligram per liter solution from OAR unit to 600 tons per day salt. And also, I would like to add one thing. The pumps and the energy recovery device are from all the pumps and the energy recovery device are from Danfoss. And I am thinking their pumps and the energy recovery device are very high corrosion resistance, and it is very suitable for the brine mining application. And these are the pictures of our commercial OAR plant. The left side and On the bottom, we have the ultrafiltration unit. On the upside, we have the nanofiltration and Seawater Ro unit. And the other pictures were taken at the actual commercial site. As you can see, our commercial plant is rarely under construction, and we are looking forward to showing the commercial operation in the next year. We also have the fully packaged OERO demonstration unit shown in this picture. The 40-feet container contains ultrafiltration, nanofiltration, Seawater Ro, and OERO unit to concentrate feed solution to more than 200,000 milligrams per liter. And the unit contains 17 pieces of Toyobo's brine concentration membrane with a membrane surface area of more than 10,000 square meters. And this is a plug-and-play unit which you can try immediately the Ferric and Toyobo's brine concentration technology at your site. So this is a specification of the fully packaged OERO demonstration unit. The overall recovery is 70 to 90%, depending on the water chemistry and also the operating condition. And when the recovery is 80%, we can get 77 cubic meter per day water production from RO. And the specific power consumption is 3.5 kilowatt-hour per cubic meter feed solution. Also, this is a fully packaged OER demonstration unit, picture of the demonstration unit. You can see on the left side, there is a nanofiltration unit and the Seawater Ro unit there. And at the right side, in the front, there is a ultrafiltration unit. And on the back side, we have the brine concentration membrane unit. And in the normal operation, we can concentrate your feed solution to around 200,000 milligrams per liter. And you can see the picture in the middle. This is a conductivity meter and showing 98%, which is around 210,000 milligrams per liter. We can concentrate. At the right side, you can see the picture in the demonstration in Indonesia. Before start construction of the commercial unit, we have performed the pilot study in Indonesia at the actual commercial site, combining with the MVR crystallizer small pilot testing unit. Through this testing, we have already confirmed we can make the solid salt from the OERO and MVR crystallizer unit from the seawater in the actual site. And also our fully packaged OERO unit demonstration unit is currently available in Saudi Arabia. And we are ready to deploy the demonstration unit in Saudi Arabia on demand. And we have the booth, AJMC booth at outside. And if you are interested in, you can contact me or come to the AJMC booth for more information. So, I'd like to summarize my presentation. Firstly, our membrane's unique configuration allows brine concentration more than 200,000 milligrams per liter, using far less energy than the conventional thermal and other membrane-based brine concentration technology. And our hollow fiber cellulose trusted membrane have unique features of very high surface area and superior chlorine tolerance to enable more rigorous membrane cleaning and stable operation with minimum biofouling. Our hollow fiber brine concentration membrane are already commercially proven and can be applied for a wide range of industries. And finally, the demo unit is now ready in Saudi Arabia for the collaborative work with the potential customers. And also, I will plan to have the presentation in the EDS conference next month, and I will make the more updated presentation for the commercial project. Thank you for your attention.
Yes, very nice to see that something now this membrane brine concentration is coming into the real life. It's very excited, and I can't wait to see the commercial plant operation next year expected.
Welcome.
I think now we have time for maybe about 3 questions. So if any questions from audience, please raise your hand, please. Actually, personally, I have a lot of questions to ask, but I want to give opportunity for the audience first. Any questions? Yes, please. Raise your hand again, please. Yes.
Thank you. My question is regarding harvesting lithium from the salts in the final procedure. So any new technology or something I can harvest or extract lithium from the last stage? Thank you.
Thank you for your question. So the extracting lithium is applicable. Our technology is applicable to extracting lithium. But basically, our technology is just concentrating the feed solution to the higher concentration. So we need the separation process before our brine concentration membrane, and pure, almost pure lithium solution we can concentrate to the saturated concentration.
Okay, next question, please. Okay. Mike, please. Yes.
Thank you very much for the nice presentation. My name is Sang-ho Lee from Kookmin University in Korea, and I'm also from TTRI. And my question is about the flux. So it seems that the flux is very low. So is there any way to increase the flux from your membrane modules?
Okay, thank you for your question. Basically, the flux is lower in the hollow fiber membrane compared to the spiral wound membrane, but we can compensate the low flux at the high membrane surface area. And also, in this application, this is not a reverse osmosis application. This is a very high salinity application. There are the issues of the concentration polarization. So the flux is much lower than the reverse osmosis also. So we are now developing the membranes with higher flux. Thank you.
Any other questions, please? Okay, yeah.
Thank you very much for a nice presentation. As all of us know that hollow fiber is very sensitive to fouling. So now you have two-side fouling possible, the potential of fouling in two sides, not only one side. What is your mitigation or cleaning, just in case, in this operation, during operation?
Sorry, I can't understand you.
Membrane cleaning, you mean?
Membrane cleaning.
Membrane cleaning strategy. Your CIP or yeah.
Okay. So CIP is one of the issue of the brine concentration process because the concentration rate is very high, and basically we are now developing the CIP process for especially for the wastewater treatment, but for the salt production case, we already developed CIP, and this is a more pure water than the wastewater ZLD system. So there is no issue to concentrate seawater to make a solid salt.
Okay, the question is because you have the flows on both sides and shell side, then in case of flushing or cleaning required, then do you clean both sides separately? Or?
Sorry, yes. We need to clean both sides. Sorry.
Okay, okay.
I cannot hear. Sorry.
Okay, thank you very much. Just maybe one last question. Okay, yeah, you have.
السلام عليكم. علي تحسين from آفاق المستقبل. I will ask the expected lifetime for this membrane first, and the power consumption. Did you have a final rate for power consumption for from end to end, from the sea to the product?
Okay. So the membrane lifetime, we do not have any long-term operation
expected
experience.
Expected.
Okay. I see. So for our reverse osmosis case, the membrane lifetime is more than 7 years. And in the salt production case, the feed water is also the seawater. So we expect more than 5 years lifetime for the brine concentrate application. And the second question is
energy consumption.
Energy consumption. Okay. Energy consumption is, as I mentioned, up to ORO, we have the 3.5 kilowatt-hour per cubic meter feed, which convert to the 4.5 kilowatt-hour per cubic meter permeate solution. And to the all the way, the power consumption will be 9.5 kilowatt-hour per cubic meter permeate from the ultrafiltration to the crystallizer.
Okay, thank you for the presentation all and the Q&As, please. Okay, the last presenter is Dr. Abdul Salem Al-Hadidi. He has a PhD degree in membrane technology from the University of Twente. He joined Fujifilm 9 years ago. Recently, he joined the technical market support team in Fujifilm as a specialist in water treatment and membrane technology. Today, his presentation is about the new concept of a salt-free EDM. Please welcome Dr. Al-Hadidi.
Good afternoon. Actually, we are all familiar with RO, and we know that for some extent, when you do a desalination, you have to deal with actually what they call it recovery. That means for 1 liter of water that you have to produce, you are producing also 1 liter of brine. I will touch today in my my presentation how brine can be managed from a technical point of view, from a technology provider point of view. I hope my presentation will be in the screen. So, as mentioned, I'm Abd Salam, working for Fujifilm. Yes, okay, thank you. So basically, Fujifilm is a provider of, or a manufacturer and supplier of membrane, ion exchange membrane, and that's why I'm here interested in your conference. This is the outlook of my presentation, and here I will give small, let's say, introduction about the brine management and why we need it, how to do it from a different perspective. I will present also our new concept called EDM, and some examples, some projects, and then I will close with some conclusions and research gap. Basically, it's a sustainable issue, economical issue. Brine management is touched a lot in many, let's say, presentations, not only in this conference, but also other conferences. Actually, it's already or always associated to RO or thermal desalination. So this concept which I will present, it's not really for RO design, but for any brine management issue. We know that RO is dominating actually the desalination. However, there is different technologies. We know the advantages and disadvantages of each technology, which I tried to summarize here. But anyway, what we know also that RO recovery is limited mainly by two factors, which one is related to the osmotic pressure that it's actually built across the membrane. The second is actually the scaling. Different technologies, different solutions actually for managing the brine when you are dealing with. If you have a chance to do a discharge to the sea or the groundwater, you will do it. You pump it either, or you maybe transport it to somewhere. But also you can use, for example, a thermal distillation or a closed-circuit RO and electrodialysis system to also deal with a recovery. However, each system has its own advantages and disadvantages, and I will focus here on, let's say, the electrodialysis part, which is actually related to ion exchange membrane that I'm working with. What's scaling? Scaling in RO or in a membrane or even in thermal, it's actually the precipitation of salt in some areas in your system, and that's actually happening when calcium, for example, here, is meeting sulfate or carbonate, then you will have a calcium carbonate, which is the picture in the left to the top. However, solubility of the salt is actually what determines this precipitation. So when you have a salt with a high solubility, you will not have easily scaling. When solubility is low, then you will have a problem. And some scaling you can clean, for example, calcium carbonate with lowering the pH, and then you are fine. Some of them are irreversible. Then when you have it, then it's done, and your membrane or system is in a very bad situation, and you have to actually rebuild it. In many cases, antiscalant can be used, but there is some limits. One is actually antiscalants are, some of them are not, let's say, environmental friendly. Some of those antiscalants, they have a limit of, let's say, working in such solubility. So once you exceed the concentration of the salt, then it doesn't work. Of course, there is a cost issue associated. And actually, our concept, which is electrodialysis metathesis, which is called EDM, is actually another way how to make a recovery of your brine without using chemicals. So only electrodialysis. And the idea or the concept is actually that you try to prevent that calcium meet the sulfate or calcium meet the carbonate. And then you create a different type of salt that has a high solubility, and then you can concentrate up. That's the main goal. EDM, which I call it here conventional EDM, it's not a new thing. It's already for years known. It's an electrodialysis system. That means you have two electrodes. You have membrane in between. Ions will be driven by the current. However, if you have modified the electrodialysis stack a bit, where you can have 6 streams, 2 in and 4 out, you may have the idea of splitting those type of cationic and ionic ions, and you can use sodium chloride as one of the streams to actually to feed with sodium and chloride ions to prevent scaling. So calcium will not meet the carbonate, but calcium will meet the chloride. And calcium chloride is very soluble, so you can concentrate up till the level that you need. That's the main concept of the EDM. And actually, in the result, in the back of the stack, you will have 4 channels, 2 dilute, and actually 1 rich chloride stream, 1 sodium rich stream. We know that this system is working, proven. However, the energy consumption is high. And therefore, Fujifilm stepped with a new concept, trying to actually lower this energy consumption. The energy consumption, or the current running through the electrodialysis stack, is in relation, or let's say in linear relation to the amount of ions that you want to transport through your membrane. If you lower the amount of salt or ions, that means you lower the energy consumption. So that means the easiest is to prevent use of sodium chloride in the EDM. But then how it will work? That's what we call a salt-free EDM. It's a Fujifilm patented concept where a special type of ion exchange membranes will be used. And it's named here CM or AM. And they are actually selective type of membranes. By using this and actually looping part of your feed in the system, you do the same trick as the conventional EDM by actually having streams where calcium and sulfate or carbonate will not, let's say, meet the divalent, but then you produce chloride rich and sodium rich. Thanks to this new concept, the energy consumption actually decreased by 50% because we are not adding salt to the system. We are not adding sodium chloride. We are using the same feed. But then you have a actually hybrid type of ion exchange membrane in one system. So this was actually an idea validated in the lab, of course, but then we went to from lab scale to pilot scale, and this is what we call it a Zelda project, where we built a unit that is working between 0.5 to 2.5 cube per hour, and actually working with brine. So this is not a desalination, it's a brine management unit, where electrodialysis, the picture in the middle to the bottom, this is the stack, electrodialysis stack, 50 by 50, with special electrodes, 300 cell per, and actually different type of membranes, as I mentioned. Basically, this is the water composition, and you see it's highlighted there in the top to the left. Sodium sulfate is very high, but also in a combination with calcium and magnesium. And if you start to, for example, use RO for this water, actually you are operating in a very dangerous regime where scaling will happen immediately. But thanks to our concept, or let's say this is the conventional EDM, then we were able to concentrate up to the conductivity of around 150, 160 millisiemens, which is very high, by the way. But also in the table you will see that concentration 1 and concentration 2, the two streams out of the stack, has a different concentration of ions. So meaning sulfate is in concentration 1, while carbonate and let's say calcium in one stream in concentration 2, while sulfate carbonate are accumulated in concentration 1. This is the whole trick. Recovery, we reach a good recovery, actually, around 80%. And actually, in this project, we try to compare the conventional EDM with our new concept. Both are working. We try to compare in a fair way where the operation settings are the same goals. And as you can see here, this is the conventional EDM performance. We have a water recovery about 80% with energy consumption around 10.1 kilowatt per cube treated water. But with actually the need for the sodium chloride stream, which is in the left side, highlighted with a red color lines. The new conventional, the new EDM, the Fujifilm concept, achieved the same concentration, the same flow, everything exactly the same, but then you will see the energy consumption dropped from 10 kilowatt hour per cube to 5.1. So you gain a lot in energy, but also in capacity, because you are not feeding with sodium chloride anymore. Another trial, what we have done is actually put RO to concentrate the feed a bit even more, and with the aim actually to increase the recovery of the complete system. And it was possible, as you can see in this picture. We had some troubles with the RO, I should admit, at the beginning, but then we figured out how to operate. We saved it from scaling because we lowered the recovery of this RO. It's a special type of RO. We are not a producer, so don't ask me about the details, but I know about the ADM, where in total we increased the recovery of the system to 97.2. All this work has been done actually in brackish water, not in a seawater at this moment. Another case study is actually with the University UTEP in the US, where two types of water were used. Actually, it's a real water, not artificial, where actually well 1 is different quality of water from well 2. What you can see here that actually conductivity-wise there is a different, but the operation settings we try to keep same. Some data from the field actually showed that current efficiency for both system, EDM and Fujifilm EDM, are comparable. Actually, current efficiency meaning that for every current that you are putting in the stack, actually how much ions you are removing compared to theory. That's the current efficiency. If you have a bad stack, then you lose part of your current. That means your current efficiency got lower. So it's not really related only to membrane, but also related to the design of the stack. We are not a supplier of the stack, unfortunately, but we have some partners working with us. We supply only membrane. For energy consumption, you see that indeed, even in US, in a different location, different water composition, we are achieving 50% lower energy consumption with Fujifilm concept comparing to what we call it STD or the conventional ADM. At different voltage or different flow, we see some advantages there. In conclusion, by using the Fujifilm EDM concept, you can lower the energy consumption by 50%. In general, as I mentioned, for brine management, EDM is working, so I don't need to repeat the conclusion here, but actually the new concept, thanks to the new concept of Fujifilm, also you lower other aspects in OPEX, not only energy, but also related to the availability of sodium chloride, transportation, etc. Water recovery is above 80%, something between 80 and 82%, but of course it depends on the water composition. So ADM in theory works fine, and it's actually giving some benefits for the operator of RO system or desalination system in general. So it's a strong reduction of waste if you are worrying about waste. Also less discharge to a sustainable reason. Reduces of or eliminates actually the brine disposal, and that's a big part of the cost sometimes in some areas, especially if you are far away from the sea. For brackish water, then this option is really good. However, I should not say that it's a zero discharge solution, but it's nearly, because still you are producing a high brine, which can be treated with thermal, for example. It's scalable, so it's a reusable byproduct. You can actually produce, or you can use this system in a good way for what they call it salt mining those days. And it's, of course, environmental friendly because we are not using chemicals. This is let's say, a rough comparison between different systems used for the same concept for brine management. You can see it's really depends on the ratio of the divalent ions comparing to your total salinity. This ratio is actually defining which technology suits your case. We saw that CCRO is working, but of course it's limited with certain ratio. So that means you have a lot of divalent ions in your water, then actually CCRO, it doesn't work properly. ADM, of course, because then there you will have a immediate scaling or RO. However, there is a moment that Fujifilm concept doesn't work when, for example, the divalent to the total salinity ratio is above 70%. Then there we need actually the sodium chloride stream, or maybe we go for thermal. At this moment, as I mentioned, we focus on brackish water because this is a big problem in the middle of the US, and they were looking actually for a solution still. So this concept validated there, and it's working. However, in seawater, we didn't try it, or we didn't continue the project there. Monovalent membranes, let's say selective membrane, are under development, so it's not really commercialized yet, but we are in the phase where we do more validation with this membrane. Fouling and cleaning of ADM system is under investigation as well, because it's membrane and spacer, then for sure you will have troubles there. But ion exchange membranes from Fujifilm actually are quite tough, so you can clean them much easier comparing to our competitors. Validation of different applications, because this is not only for desalination of water, but it can be used also for other applications or industry, like produced water, or actually food and beverage, or other applications as well. And the scale up of the industrial level, that's our aim now to go on that direction. I need to thank actually UTEP, our partner, who actually has done the part of our work, and also the ZELTA project, subsidized by EU, where we also produced part of the data presented here under the umbrella of ZELTA. With that, I would like to thank you very much. It's not a very detailed presentation, I can imagine, but I'm available around if you have any question, a technical question, I would be happy to discuss with you. Thank you very much.
Thank you for the presentation. It's great to see that you could save almost 50% of the energy compared to the conventional ED in the brackish water application. Any questions from the floor, please? Okay, yeah.
Thank you very much. I have several questions. First question, what is the salinity of the dilute that you have? This is for brackish water, so I assume you start with around 10,000 ppm?
Yes, so basically, as I mentioned, it's a brackish water, so it's up to 10 millisiemens. That's the worst case that we handled.
And the dilute that you produce, what is the concentration of that? The dilute stream?
The produced water.
No, the dilute you produce.
Dilute, yes, that's a produced water. So basically, we started with, in one of the cases, I can maybe go back.
Just tell me a number and that's it.
Yes, so basically this example is where we have 6.5 gram per liter in the feed, and the dilute was around 2 gram per liter.
Okay, and when we say an energy consumption of 5.5 kilowatt hours per meter cube, is it meter cube of dilute?
No, it's a feed.
Meter cube of feed?
Yes.
Okay, so it's half, almost half. I don't know, you have a recovery of 80%, so it's about, yeah, okay. So
Yeah,
divide by
because
0.8.
the focus
Okay,
here,
got
sir,
it.
is not really to produce a diluent.
Okay.
The focus is to concentrate up, so it's a concentrator system.
Okay, I understand. And now the next question is about your setup. You have 6 compartments. How many kinds of membranes do you use there? Is it only 2 types, or you have more than 2 types?
Basically, ion exchange membrane works in pairs. So you have anionic exchange membrane, cationic exchange membrane. This is the conventional membrane, but also what's mentioned with M, this is a selective type of membrane. So you have AM standard, CM standard, AM selective, CM selective.
Okay, so you have 4 types of membranes in there.
4 types of membranes.
Some of them are monovalent. They will allow monovalence, and others will allow divalence to go through.
Yes.
Makes a lot of sense. That's good. Thank you. And then you said you managed to reduce the energy consumption by 50%. How did you do that? Do you make thinner? Are your membranes thinner, less? They have smaller cross section, or thin membranes, or what? What is the idea?
Ion exchange membrane, let's say that we produce in Fujifilm, we have this conventional membrane that has a very low electrical resistance. That's the actually beauty of this membrane. However, here in this concept, we lower the energy consumption by eliminating the need of sodium chloride. I said in my presentation that the relation between the current or the energy consumption and the amount of ions that you need to transport through the membrane is linear. By adding sodium chloride to the system, you are already eliminating the need of energy for the transportation of sodium chloride.
Thank you.
Welcome.
Any other questions from floor, please? When you have question, please name and occupation.
There a question?
Hi, I'm Fadi Saleh from Matito. I have one question. Can we utilize it in brine concentration for seawater applications? And what is the limit on the concentration side?
Basically, we produce different type of membranes. We produce tailor-made of membrane for different technologies. In terms of high salinity, our experience now up to 200 millisiemens, that we can concentrate up to 100 millisiemens, coming from 30, 40 millisiemens in the feed. I would say it's more in the energy side more than the technical issues, this limit. Our membrane has a different water permeation, so we designed the membrane to fit the concept here. So we use also a special membranes that has a low water permeation, because once you concentrate up in one stream while your diluate has a low concentration, you are building osmotic pressure across the membrane. You start losing water from the diluate to the concentrate. If you manage this water permeation to be low by actually changing the parameters in the membrane itself, you gain a lot. If you can do it also in the process by basically you play a bit with the pressure in the system, that you avoid the water permeation goes from the diluate to concentrate, even it's better. So for seawater, we have a lab scale systems. It works, and we can, as I mentioned, we can go from 30 millisiemens up to 200, but we didn't do a pilot test yet. So we are only in the lab scale.
Clear, thank you.
Yeah, we have one more question there.
I'm Dr. Ghulam Mustafa from DTRI. Just wanted to know that while concentration...
Can you put the microphone a bit closer?
Okay. While doing the seawater concentration up to 200 millisiemen, how much energy will be required? How do you feel, Miss, how much will be energy requirement?
I don't have the number on my mind at this moment. I can share it. I can share it with you. However, it can be also even simulated. I can calculate it because, as I mentioned, the current, the relation between current and energy is linear. So more ions you transport, you you lose energy. However, I would say on the range of 16 to 20 kilowatt hour per cube. But this is, as I mentioned, it's really a simulation data.
And I believe there is no effect on EDM.
Sorry, can you?
I believe there is no effect of presence of organics in the on the EDM.
I didn't
presence
get
of
it.
organics presence in seawater.
Organics are present in seawater.
Okay. Yeah, so basically, as I mentioned, fouling is an issue on all kind of membrane technology. However, the only advantage in EDM or in ion exchange membranes, mostly it's a tough membrane comparing to RO. In RO, you are dealing with a very thin selective layer. Any mistake, then you damage it immediately. Ion exchange membrane are 150 micrometers in average, 100 to 150. And then you have a room to actually to have a very aggressive cleaning regime. So then you can manage the ion exchange membrane or EDM system much better than RO. So that means you need less pre-treatment comparing to the RO in EDM, for example.
Okay, thank you very much.
Okay, thank you. I believe now time is over.
Thanks.
Big applause again for Dr. Al-Hadidi.
We're now moving on to a coffee break from 3 to 3:30. We'll see you back here for more exciting presentations at 3:30. Thank you.
Thank you so much to our speakers and chairs. What a wonderful session, and thank you to the audience for really engaged questions. I may actually have to contradict the coffee break suggestion, which was originally planned, because we have a really exciting upgrade to the program this afternoon. If I could ask our chairs to make their way back to the audience, thank you. We have some MOUs and agreements that are now going to be signed. And so, for the first 4 of these MOUs, we have some guiding objectives that I will share with you now. Firstly, these MOUs are about studying the data and presenting an integrated plan for innovation, localization, the transfer of knowledge, as well as developing a training program in order to contribute to raising the efficiency of knowledge amongst workers in the field of manufacturing cartridge filters. Very important work. So, to represent SWEC for these 4 MOUs, may I invite to the stage, please, Engineer Abdulaziz Al-Babtain, Deputy Governor of Planning and Development at SWEC. Thank you for joining us, Engineer Al-Babtain. The first MOU that will be signed is between SWEC and Veolia Water Technologies. So may I please invite to the stage Dr. Ahmed Gawaji, CEO of Veolia Water Technologies. Congratulations to both institutions on this wonderful new partnership. If I could invite Engineer Abdulaziz to remain on the stage, we'll announce the second MOU between SWEC and the SAMNAN for Operation and Maintenance. Therefore, could I please invite to the stage Engineer Abdulatif Al-Abdul Karim, CEO for SAMNAN for Operation and Maintenance. Congratulations to both organizations on this new partnership. As I invite Dr. Abdulaziz to remain on the stage, I will announce the third of these 4 MOUs. This is a Memorandum of Understanding between SWEC and the Al Khortha Company, and therefore may I invite Mr. Walid Hambishi, CEO of the Al Khortha Company, to the stage. Congratulations on this new partnership. As I invite Engineer Abdulaziz to remain on the stage, he will sign the final MOU in this series. This is a Memorandum of Understanding between SWEC and the Saudi Salwa Company, and therefore I would like to invite to the stage Engineer Nabil Turkestani, President and CEO of Saudi Salwa Company. Congratulations to both organizations. I invite both signatories to take their seat, and we have 3 more to sign. All 3 of these are between SWEC and the King Abdulaziz University. Therefore, to sign the first 2 on behalf of SWEC, I invite Engineer Khalid Al-Jandal, General Manager of the Project Engineering of SWEC, to the stage. The first of the 2 agreements is a research agreement for installing floating solar photovoltaic in dams between SWEC and the Center of Excellence in Desalination Technology of the King Abdulaziz University. Therefore, to sign the first of these two MOUs now, I invite Dr. Hani Abu Khair, the Director of the Center of Excellence in Desalination Technology at the King Abdulaziz University. Do we have Dr. Hani in the audience, please? If not, perhaps, Engineer Khalid, we can move to the second of your two signatories. And therefore, I'd like to announce a research agreement. Oh, perhaps we have. Dr. Hani, welcome. Thank you so much. Let's celebrate this great new partnership. Thank you so much. And as Engineer Khalid stays on the stage, I would like to announce the second of his signatories this afternoon, the research agreement to study and find solutions to the phenomenon of the tide in the Red Sea between SWEC and the College of Marine Sciences of the King Abdulaziz University. Therefore, I would like to invite to the stage Dr. Adnan Turki, Dean of the College of Marine Sciences at King Abdulaziz University. Let's join together and congratulate the two organizations on this new partnership. Last but not least, we have one final agreement, a research agreement for the comparison study of different methods of assessing occupational health risks between SWEC and the College of Meteorology, Environment and Arid Agriculture of the King Abdulaziz University. Therefore, to represent SWEC, I would like to invite to the stage Engineer Marwan Salangur, General Manager of Industrial Security Department at SWEC. To represent the College of Meteorology, I would like to invite to the stage Professor Adel Al-Karashi, Dean of the College of Meteorology, Environment and Arid Agriculture. Let's join together in congratulating the two institutions on this great new partnership. It's wonderful to see all of these partnerships springing up and signed here at the conference, and really reflective of everyone's passion for innovation and moving that forward for good outcomes in the water sector. Please do now enjoy the coffee break, and we will resume at 3:30 for the final session today. Thank you so much. To take your seats as we come together for the final session of this opening day of the Innovation-Driven Desalination Conference. Well, welcome back, everyone, to the next phase of this important conference on innovation-driven desalination. Ladies and gentlemen, I hope you feel refreshed from your, albeit rapid, coffee break, because we are finishing today on a very high energy and interesting session. Our topic this afternoon is digitalization in desalination. We know that we live in the digital age. We know that other sectors maximize the benefits from digital. Desal does some of it already, but how can we increasingly innovate and have the innovative mindset to really make the most of this great tool for progress, efficiency, and delivery? This is what we're here to address today. So with this in mind, it's my great pleasure to welcome to the stage our session chair, engineer Nikolai Vuchkov, senior expert at DTRI SWEC, and Mr. Christos Karisiadis, Innovation and Business Development Manager at Lentec, the Netherlands. This session is due to conclude at 5 p.m. Gentlemen, you have the stage.
Thank you, thank you. Thank you and welcome to the afternoon session of digitalization of desalination. And the focus of this session is to look at where have we moved into digital age and what type of applications we have been working on in that field. We do have 3 speakers that address various issues of digitalization of desalination in order to improve energy and efficiency of the systems. The very first presentation is from Norway, from Alexander Fusenang, who is founder and CEO of F-Subsea, a Norwegian company specialized in subsea systems. Norway is the most famous in Europe country for deep ocean exploration and also for deep oil exploration. So many technologies have been developed to explore oil resources in deep seas. That technology is being brought in to bear in our industry, desalination industry, to use some of the equipment and facilities created for the oil exploration industry to actually explore deep desalination. Desalination plants that use the available static energy of the ocean column to reduce energy of desalination. Our presentation is with a company which is Oslo-based, over 150 years old company in Oslo. And he has many passions, ocean and business together. He's a co-owner of this company called Subsea in Norway, and they're specialized in very interesting, innovative technologies for deep pump, especially high-pressure pumps are important to us. And he has an elegant solution of sealless pump that eliminates the issue of water penetrating into the pump. And other issues with focus on the presentation today being actually a subsea system that can be allowed to adjustably use the pressure of the ocean column to produce desalinated water at breaking low energy. With that, I would like to introduce Alexander.
Thank you, Nikolai. It's a great pleasure to be here. Thank you for inviting me, IDA Committee, Your Excellencies. I am Alex Fuglesang. Thank you for the nice introduction. I am very passionate about this topic, and I'm talking about 2 things, really. One thing is deep water desalination and what good that can do for the community. And I'm also going to talk about digital twins. So hopefully you have something to take away from this session. The presentation is scheduled to, as me going through a little bit of a background, as well as some challenges, and then moving on to solutions and what good that can do for us in terms of benefits. So Nikolai pretty much covered the basics, but we are an old company, and I'm not going to bore you with the full 150 years. But the last 40 years have been centered around advanced pumping technology and process systems. And the last 15 years, we have been operating beneath the seabed, the sea level for oil and gas and also other applications. We celebrated recently our 50th system, so we have 50 or 50 systems operating in the seas around the world. And we've also helped oil and gas industry with seabed water treatment applications and supplied more than 3 pumps for innovations during the last 7 years. One of the challenges that has been talked about today is the pre-treatment area, and typically there are more than 16,000 RO plants around the world, and pre-treatment takes up a significant part of the plant area. It could be 40, could be 60% of the plant area if you take the intake as a part of the pre-treatment. And every plant is different, and very often the pre-treatment is sized according to variations which are things like algae blooms, which can happen in a 4-year cycle. It can be one big algae bloom, for instance. So you're designing the plant for events that happen rarely. And it's not just the pre-treatment part, but there's other parts of both the CapEx and the OpEx of a plant which is not optimized. And a lot of this has to do with the organic content of the feed water. It has to do with impingement, entrainment at the intake. We have challenges with energy consumption. Even RO is better than MSF. There's still excessive energy use. And we're using a lot of chemicals and land resources for the plants. So we think this can be improved. And so this is one of the reasons why we're looking together with SWIC, and we've done a project together looking at the benefits of going deeper. And there's several approaches to this at the moment, and we've really looked just at the basics and thinking about first principles. So once you go deeper, you really get access to a more predictable, and that's really the key word, more predictable, stable quality water. It's more consistent quality and temperature. And you also get a lot of these precursors to biofouling, like biopolymers and bacteria and algae are not present because you're below the photonic zone, so there's no photosynthesis. So that creates a lot of benefits. And lastly, you also have nature working with you in terms of a high hydrostatic head that Nikolai also mentioned. There, you can use that pressure differential for something beneficial. And we'll come back to that in the system. So if you remove all these precursors, you can take away a lot of the steps traditionally involved in pre-treatment, and you get longer lifetime out of your RO membranes and also the different other parts of the system. There's also less organic growth on equipment when you're not in the photonic zone of the ocean. So this brings a whole host of benefits, including less energy, and more sustainable in terms of the marine life, less OpEx, less CapEx, and you're not using land, as well as you are protecting your facilities in a more direct way when you're putting them on the seabed. So this might sound strange to you that we're putting all this equipment on the seabed, but it's not actual rocket science. The technology is there, and a lot of these components don't really care if they're on the surface or if they're on the seabed. So while I would love to go through all the technology in a huge amount of detail, I think we can go through some of the principles. So I think one of the basic principles is we need some kind of filtration that will always be depending on the different project where you're located. And there will be lots of different opinions on the pre-treatment. We will have the pump on the seabed, and the main pump is, which is traditionally the high-pressure pump pushing seawater onto a reverse osmosis membrane. If you're on the seabed, we can actually have the main pump doing the heavy lifting on the freshwater side of the membrane, so we can suck the water. And I'm going to point a little bit if this thing works on the screen, I'm not sure. But if you look at the system up there, and the pump to the right, the permeate pump to the right of the RO membranes, that's actually sucking through the membranes. And we cannot do that on land because the pump would cavitate. But when we have, say we're at 500 meters and we have 50 bar hydrostatic head on the inlet side, the feed water side of the membrane, we can suck through the membrane with a pump, a permeate pump, downstream the RO membrane. And that permeate pump is obviously just pumping permeate, so it can be a lot smaller than if you had a pump on the seawater side, which is pushing the seawater. I'm hoping to get some questions later on this if somebody is struggling with the details on that. But that's a very simple, but that's in its purity, that's what's going on. So that's where the energy savings come from, and we don't need an energy recovery system to get the energy savings. So some of our technology is around having equipment that can be installed and you can forget about it, because once you're in this environment, you don't want to have maintenance too frequently. You can still have maintenance. In the oil and gas industry, we have standardized that between 5 and 10 year maintenance intervals. So that's what we're looking at here in terms of the equipment. So it's not going to be there forever, but you can. But the oil and gas industry over the last 5 decades has been on the seabed. So there's been a lot of technologies implemented to do this. So you see downstream, you can remove a lot of the processes from the intake and the direct, the flocculation and the dual media filtration, the UF and the NF. You can considerably cut back on that onshore. And so it's an easy way to add capacity to an existing plant, or you can build a greenfield new plant like this. And being in the ocean, you can also access some of these great renewable technologies like tidal power, floating sun, and other renewable technologies that can make this system completely self-sustained. Of course, it's also possible to bring a power cable from shore, which is conventional off-the-shelf cables that is used in the industry today. So we have designed a concept together with SWIC to just show you the whole idea, and it generally shows a few modules, depends on the size. We went for a 50,000 cubic meter per day system, which is totally attainable. The different players in the industry are looking for that size when they're doing concept studies. And we can really make it larger or smaller. It really depends on the redundancy requirements and what sort of minimal operational standards you would like for the system. And one of the beauties, I think it's been communicated by the industry previously, is looking at the process and based on the technology, because all these components that go into this technology is actually known, that there's no rocket science or new qualification going on. You can go down to below 2 kilowatts per hour, 2 kilowatt hours per cubic meter, which is pretty much unheard of yet in the industry, at least at scale. You also get much more diluted concentrate because we can run at lower recovery rates. We basically have seawater all surrounding the system, so you can run at low recovery and have a longer lifetime from that perspective of the membranes. And you can then also have a more diluted concentrate on the seabed. So this is really pretty unique. We can remove the chemicals, and off we go. One of the things that we can do when we do new things, which we can do now, which we couldn't do sort of 5-10 years ago, is that there's a whole host of tools available to the industry to model. And one of the things we looked at is making a digital twin. And that's a buzzword right now, so lots of people just raise their eyebrows and are not, and I understand that, because digital twin can mean a whole lot of different things. So in this context, I'll try and go through what it means for us and what good it can do. So a digital twin is really, a virtual copy or a replica of something physical. So we went ahead and we built a virtual model of a physical plant. Either it could be a pilot plant or it could be a full-scale plant. When we did this, we started off with a pilot, and we also have done the model for the full-scale plant. So if you look at that lower blue line here, which I'm not sure you can read the fine text, but the first thing that building a model can do, when you put the mathematics and the process simulation behind it, is it gives you a very good graphical representation of what's actually going on, and you can play around with the different inputs and control knobs. But it really then makes the whole, and you can make a plant fully operational before you've even designed it and built it. So it takes down the risk and makes the plant design much faster and much better and much more effective. And the probability of getting it right the first time you design the plant is much higher. So this goes for a subsea desalination plant, but it's the same for an onshore desalination plant. So that's the first step. And then once you build something, you build a physical prototype or a pilot, in this case, in the subsea. A lot of clients want to see a pilot. And then you start getting actual data. So then you start to feed back that actual data back into the digital twin. So and you optimize the model that you had from, and whether that model is made in MATLAB or Python or HYSYS or sophisticated simulation software, it doesn't really matter. But it continuously make your model much better. And then you have a representation which can be viewed not just by the researchers and the doctors, but also by the business people and the commercial people. So it's a much more, it's a much improved way of communicating. And then once you start to get real data and you do this full circle again with a full-scale plant, then you can actually start to add technology like artificial intelligence and machine learning. So you just increase the sophistication of the mathematics, whether it's heuristics or neural networks. You apply mathematics, and then you will get lots of input on how you can improve your operations to improve efficiency. Or you can get input to how to predict failures. You can see that if you're running it at a certain duty point, your pumps will not last as long, so you better reduce the speed of the pump by 10%. Then you have a remaining useful life of 5 years more or something like that, or 2 years more. So you can get all this data once you start getting into this world. And the tools are out there to do that. And we've been part of doing it for the industry, and now we hope to help in subsea desalination. Let's see. One of the cool things is that we actually have this model here. This is a static presentation, but we have at the SWIC check-in counter, just out here and to the right where you came in, there's actually a model running, the model I'm talking about. And you can play around with starting and stopping it. There's a button there for maintenance, so you can see how one of these modules get pulled up onto the surface for maintenance. And you can see how changing the variables, such as the depth or the speed of the pumps or other controls, will alter the output, which of course is your permeate. You can see how the salinity of the concentrate changes, the salinity of the permeate. And so it's a pretty cool thing if you want to see how this works in real life. So I really encourage you to come and visit over there. A little bit of a sneak peek for those who are interested. I'm not going to dive too much into detail, but behind the scenes here is not just a couple of lines of code, and it's really how complex you want to make it. So we modeled different desalination plants and with different conditions on the inputs and different control variables. So this is just how it kind of looks in a 2D form. But this is a multivariable dynamic simulation. And you can have one dimension or several dimensions to those simulations. But that basically drives the digital twin visual part from the back end. Let's see. So to try and summarize, there's some short-term benefits getting into the digital twin area of things, and there's some long-term benefits. I think in the short term, getting started with projects, and again this goes for onshore as well as subsea, it's much faster. You can build a model of what you're trying to do, and you can actually start up the plant before you even make an investment decision. So, you're able to communicate through an organization much more efficiently and understand the risks and the implications of what you're trying to do. So it's very powerful from that perspective. And that takes down your technical risk and your initial cost, or the CapEx. Over the long term, that's where all the nice benefits and the big benefits come when you start implementing AI and machine learning into really driving up your performance or improving on your reliability planning and maintenance planning. And thirdly, I think an overlooked part of this, which is attainable both in the short and the long term, is the business model. Once you have data representing the asset, the plant, you can actually align yourself, if you're an operator of a plant, you can align yourself with the supplier in a much more powerful way. Because usually the supplier wants to sell something expensive and they want to sell spare parts, and then the client, the end user, would like to have something that lasts forever, and they don't want to buy more expensive than they need to. So the goals of the supplier and the customer are not aligned traditionally. But with this tool, the supplier, if the supplier can get the data from the operations, they know that the customer is treating the system well, and then the supplier should be able to price the system more on a per-use base. So you can actually buy the equipment, much cheaper, but you have to, as an operator, but you have to pay the supplier once you're using it. And that means everyone has an incentive to make sure the equipment is working reliably. And so you're in the same boat. So this tool can make sure that happens. And that's an incredibly powerful part. So I'd like to thank you, and I'd like to help, and again, encourage you to be inquisitive and come and see the model. Thank you.
Thank you very much, Alex. And we would like to ask you if you do have any questions. It's an interesting concept, trying to use the natural pressure that ocean can offer, and also to minimize pretreatment and, more importantly, minimize maintenance. This is fully, from what you presented, this is a fully unmanned system. So, any questions to Alex? Yes, sir. Please go ahead.
Thank you for your presentation. I'm Joab from WEG, Brazil. When you mentioned the subsea system, the pump, it's a pump, a motor, and a drive it as well, or just motor?
Thank you. It's a good question. No, so the pump is a electrically powered centrifugal pump, and usually they are liquid filled, so you can put them at any depth, and it doesn't care because it's pressure compensated to the ambient environment. And there are different technologies as well. We want to make sure there is no barrier fluid, typically that you have with pumps and seals, so that there's no chemical leaking into the ocean. And one of the technologies we have for that is a magnetically coupled pump. So there's a wireless transfer through permanent magnets between the motor and the pump, so there's no mechanical seal. And there's other elements to this as well, but so I don't know if that answered your question.
The motor is a permanent magnet motor?
No, well, the motor doesn't need to be permanent magnet motor, although those exist, but the connection between the motor and the pump is a magnetic coupling. But you could also use a PM motor, but that's more expensive, so you don't need to do that.
Okay, any other questions? Yes, please.
Hi, thank you, Arjen Nederland. How deep are these units?
So typically we're starting out with kind of what's the optimum, and optimum depends a little bit on salinity and temperature and so on. But in general, I would say the optimum is around 400 to 500 meter water depth. That's where you are above the osmotic pressure of the seawater and the inefficiencies and so on. So you want to have at least 40 to 50 bar of a hydrostatic head to have the most energy efficient system. But you can already start getting benefits at more shallow water, And you can go deeper as well, but then you're losing, you need to pump the water back up, so you're starting to kill your own benefits by going deeper than the 500. And in the oil and gas industry, for 3 decades, we've been having rotating machinery down to, well, in the last 10, 20, 15 years, down to 3,000 meters. So 500 is not a complex thing from perspective of equipment available to do it.
One more question for you. How do you compensate for the temperature variations?
So I think every location has its intricacies, and temperature is, of course, one of them. And so usually what we see is on the subsea, there are less variations. So it's an easier job to compensate for temperature variations than you would have onshore. But you need to design the system so it can get the output that you need at the right temperature. I don't know if Abdullah, if you have anything to complement. Is he there? There he is.
Thank you.
He's part of the project, yes.
Okay, regarding this, actually, there is some data we refer to with our partner in KAUST. At some depth, usually the temperature is constant all around the year. For example, in the Red Sea, for example, opposite to Rabigh Swik facility, let's say at 300 meter depth, the temperature is around 22 to 23 year round. It's constant temperature. So I think this is one of the most powerful points for this project. So you don't need to take care of temperature variation, but you still have to add some like safety factor in the system. Actually, we are talking about something below the thermocline, because after the thermocline there is no sunlight, and the chance for deep currents are low. So we are talking about almost constant temperature based on the data we have with our partner in KAUST. Okay.
Okay, thank you. Thank you very much, Alex. And you will always have the opportunity. It's an interesting topic, very unusual, very innovative. You will have the opportunity, if you go to where you checked in this morning to get your badges, there is actually a display and working model of what was presented. So if you'd like to learn more about it, Abdullah will be there, and Alexander will be there to give you a demonstration. With that, I would like to invite Christos to present the next speaker.
Thank you, Nikolai. Ladies and gentlemen, I would like to introduce you our next speaker, Khalid Al-Saif, who is a TNI senior engineer with SWCC. He's going to give a presentation on intelligence, collaborative diagnosis, support system for desalination plant PLCs. Khalid has a wide knowledge and 22 years experience on field instruments, control systems, mobile application development, M-learning, data engineering, deep learning, and web development. Khalid is currently a senior engineer with extensive experience of the supervision of satellite desalination plants for INC projects. Khalid? The stage is yours.
Yeah, thank you, ladies and gentlemen. Nowadays, SWCC has come a long way with in digital transformation by emphasizing the innovation, which is an essential element of digital transformation KPIs that leads organization to achieve the goals and vision. I'm Khalid Al-Saif, Master of Computer Engineering. I'm going to present the diagnosis intelligent collaborative diagnosis system for desalination PLCs. So briefly, I will go through these headlines. Some definitions in this section of the introduction will be provided, and I will clearly provide the aim and 3 objectives of this paper, and how the traditional literature review is done to obtain the research gap. Besides, the paper methodology and design are discussed with high-level architecture of the systems, and to prove our concept, we have implemented a prototype, and we have got the result and findings which have been addressed for the research paper. Moreover, for this related future work is investigated. And finally, I will go through the demo. So, as an introduction to this paper, the definitions such as diagnosis support system, AI, machine learning, and deep learning, BLC are presented, where the diagnosis support system is defined as an aid tools that can be diagnosis, troubleshooting the fault of any type of systems in the industrial domain to prove the right solution to the user. And there are three different types of the diagnosis support system. The first one, we call it collaborative diagnosis support system, which is an interaction between the user and the machine. The second collaborative or the second diagnosis support system, we call it distributive diagnosis support system, which is an interaction between the machine to machine. And additionally, they're capturing real data from other systems. The third one is called hybrid, which is a combination of collaboration and distributive. So as shown in the Venn diagram, AI is a broad field that includes machine learning and deep learning, and is defined as the machine that performs functions that require intelligence when performed by humans. Also, we can see the machine learning is a subfield of the AI, and it's defined as a study of computer algorithms that improve automatically through experience and the use of the data. And finally, the deep learning is defined as a subfield of machine learning in which multi-layered neural network learn from large data set. So as a case study, to apply the diagnosis support system, the BLC control system has been used. And as you know, it's a special form of microprocessor-based controller that uses programmable memory to store instruction and to implement functions such as logic, sequencing, timing, counting, and arithmetic in order to control machines and processes. And it has four major components: CPU, I/O, and communication card, and power supply. So applying this case study gives us ability to achieve our aim and three objectives. So our aim is to provide the most accurate model by generating a synthetic faults data set for the intelligent collaborative diagnosis support system for BLC in the problem domain of the industrial corrective maintenance. And there are three concerted objectives. First one is to optimize the maintenance cost. Second, to reduce the downtime of the equipment. Third, to apply the knowledge transfer between the workers. So in this section, the literature review or traditional literature review is done based on two aspects. We focus about all studies which were focused on the diagnosis support system in both approaches, predictive and corrective maintenance, in collaboration manner. On the other hand, we highlighted the distributive approach of diagnosis support system. So the comparison table was created and classified based on added value of the research and which type of algorithm in diagnosis support system has been used. Additionally, the research gap of each certain paper and what are the limitations of those research. Consequently, a taxonomy graph is provided to classify the previous research in terms of using machine learning and the type of diagnosis support system for either collaborative or distributive approach. Moreover, in which type of maintenance that tackle, for instance, corrective or predictive maintenance. By obtaining our research gap and research taxonomy, we come up with two research questions. The first one is how to provide a model with an appropriate algorithm with high accuracy result to apply it in diagnosis support system. The second question is how to generate synthetic data set of BLC faults due to the lack of data sources to improve our model accuracy. So according to our research gap, which has been identified in the literature review, and the defined research taxonomy, a high-level model architecture is developed by applying the most right-accurate algorithm in diagnosis support system and by collecting and generating the synthetic BLC fault datasets. We can see here the high-level architecture of our model. So there are 3 or 2 actors. Each one has a significant rules. So the engineering user, as you can see in the left side, he can access the system, interact with the system by troubleshooting and diagnosis the fault, which is stored in the data repository. And these data sets are injected to the model to be trained, validated, and tested. Ultimately, prediction is done. In case if there is no prediction is provided, the system will keep the fault as an open status until the external expert user provide the right solution. Therefore, a collaboration concept is applied in our model, although due to the lack of data set, we could overcome this challenge by generating a synthetic data set which enhancing our model and accuracy. So to prove our concept, a prototype model is implemented, and by using Siemens BLC SIMATIC S7 with different type of faults, we classified it in 4 classes. The first fault, which is a CPU failure. The second fault was power supply failure, and communication failure, as well I/O cards failure. So we have developed 2 types of models. The first model is created by AutoML, machine learning. We use the natural language processing. The second model is created by using Python library, which is called skitlearn, using decision tree model. So due to the obtained confusion matrix, we had less accuracy in the first model, and we have gotten an improved accuracy in the decision tree model with 65%. So as a conclusion, this paper introduced an intelligent collaborative diagnosis support system for control system in desalination plant and type of corrective maintenance. The second is the proposed model is chosen based on the most appropriate machine learning algorithm to provide an accurate outcomes based on the data sets are selected. Another challenge is discussed is how to generate the synthetic BLC fault data set from different fault data sources. Also, the implementation of the model is provided and comparison results based on different algorithms are used. Last but not least, the security issue and how to implement the model with the respect of securing the data between OT and IT. It can be future-related work. So this is a demonstration for our prototype. You can see here, this is the assets which the user can create, or it can be integrated with any type of ERP system. He can describe the assets or the device which we want to add it in our database. Then he can add the fault related to that asset. Once he completes this creation of data device or data or assets of the systems, then the system can provide the prediction for any faults related to that asset. So we can see here the prediction fault. It is a power failure when the symptoms of the problem is mentioned according to the fault description. The second prediction was in the I/O card where the symptoms of the fault related to that. So the system analyzed the error based on the AI or artificial intelligence, depending about the data set. We can see here the faults. The user can list all the faults, and he can see which one is an open status so the expert guy can access the system and he can close the fault, and the other user can interact with the system, and the prediction or the accuracy is increased. So eventually, AI is one of the Industry 4.0 core technologies, and applying those technologies can enhance the impacts on our societies, resulting in economic, social, and environmental benefits, and hence more sustainable society. And thank you very much for attention.
Khalid, I would like to thank you very much for the wonderful presentation and for staying within the time presentation limits. At this point, I would like to ask our esteemed guests in the audience to ask any questions to Khalid concerning his presentation.
I have a question.
Yeah, sure.
Have you implemented this in any particular plant in SWCC, one of the desalination plants? Have that been implemented at this point, and what is your next step?
Yeah. Yeah, in fact, it's a prototype which we can test our concept. So in future, we have to integrate it with some ERP system to have more data, because one of the big challenges that we have list of data set. So once we get more data set, that the system can interact in the proper way and give more prediction to reach the desired need. Thank you very much.
Khalid, I would like to thank you very much for the presentation. I would like to I'll let Nikolai present the next speaker.
And our third speaker for the day will be addressing an interesting topic about the use of VFDs. VFDs are used almost everywhere in desalination plants. And his name is Joel Alves. He received his PhD and Master in Science degrees from the electrical engineering from the Federal University of Santa Catalina in Brazil. And currently he works for a company, WEG, which is specialized in development of variable frequency drives for low and medium voltage motors. So he will be discussing latest developments and achievements in that field and uses in desalination. With that, I would like to ask Joel to join us.
Good evening. I just arrived 2 days ago from Brazil, so I'm trying to learn. This is my first time in Saudi Arabia, so I'm learning some words. I should say, Assalamu alaikum. Sorry for my pronunciation. I was here since the beginning of this morning. I have learned a lot. Because I'm from the electrical field, I'm not from chemistry, so thank you very much for the previous presentations. I've learned a lot, and congratulations for SWCC for this organization. It's great. Thank you very much. I was reading last week about some part of the world is looking for a journey to Mars, and I thought to myself, what exciting this journey to Mars, because probably they are looking for water there. I don't know. I hope they find the water in Mars. Nothing against Mars, but congratulations to Kingdom of Saudi Arabia to looking for water here. I think it's a good idea right now. My presentation is regarding to modulation techniques. I'm trying to do some correlation between the field of water and the electric field. If you have questions during this presentation, please, at the end, we will be happy to clarify. So let's move forward. So my company is specialized in motors and drives and automation products. We are happy to say that we have some equipments here in Saudi Arabia, in Habib 3 plant, which is a proud. We don't have, nowadays, in our mind in Brazil, problems with water because we have a plenty of water there still. But I think this is going to be different in the future, in the soon future. In the electric equipment, as the power increase, we have to use medium voltage components. Let me do some brief explanation about the converters. All electrical equipments are looking for a perfect waveform in terms of voltage. It's a correlation with fresh water. The equipment is looking for a fresh water. From the electrical point of view, we are looking for a sinusoidal waveform in terms of voltage. As the technology is advancing it more and more, we are using semiconductor to adapt this available voltage, which is sinusoidal. The grid is a fixed speed, fixed amplitude. So we need to convert this energy for a proper energy to the end user, like a pump, if you want to control, for example, pressure. So this converter has this function to do this adaptation. As the power increases, normally you have to increase the voltage as well to keep the currents at certain level to not increase the cost of the installation. So semiconductors, as the name said, is a switch that works on and off. It's like a switch, on and off, to adapt and transform that energy into a usable energy. So one of the main concerns is during this switching on and off, it causes losses. So we have to reduce as much as possible these losses to keep our equipment in a efficiency level that is available to the system, because if you are going to use equipment, you don't want to increase the losses. So one concern is regarding the switching losses. Another concern is regarding to how we can deliver energy in a more waveform, sinusoidal waveform to the motor, for example. So the figure of merit is the total harmonic of distortion, TAG. So we are trying to look a perfect waveform, reducing the TAG. The TAG, the best TAG is 0. It means no deformation of the waveform. The motor will not feel any kind of additional losses, any kind of torsional vibration, as the converter is not present there. So this presentation talks about methods of how to control those semiconductors, as we call modulation technique, looking for the best trade-off between minimal losses, best waveform. So our engineers, using the math, was this equation, which is known as a Fourier equation, and the algorithm, the computational algorithm, looking for the best combination according to optimization of the waveform. So this graph shows, for example, two modulation techniques. OPP stands for Optimal Pulse Pattern, and SAG, which stands for Selective Harmonic Elimination. You can see two methods of modulation. In the ramp, close to the wall, you have the energy, which increases as we increase speed or torque. And the mountains, the small mountains in the graph, in the 3D graphs, represents the harmonics. So those harmonics are not desirable. We want to eliminate or mitigate, reduce as minimum as possible. If you can reduce, the waveform of the voltage at the motor terminals will be very sinusoidal. So why I am presenting two modulation techniques? Because depending on the application, one or other is more suitable. So this is a basic diagram of variable speed drive or variable frequency drive. It starts from the main grid, the power supply. Normally, for medium voltage systems, we use a transformer. Increase the number of secondaries of this transformer to reduce the harmonic content from the point of view of the grid. 12 poles, 24 poles, 36 poles. Increase the number of poles, which means more secondaries in the transformer side. You can reduce the harmonic content from the point of view of the grid. The semiconductors with rectifiers like diodes and switches like IGBTs, MOSFETs, and then your machine, the motor that will drive, for example, a pump. So I'd like to share with you how we can work with the development of such modulation technique. We start with simulation parameters. We start with, our engineers start with scale prototype using simulation parameters. Here are the variables for all the internal parts of this converter. And then we can create, by simulation, the waveforms. So you can see two waveforms, one produced by OPP modulation and the other by selective harmonic elimination. It seems similar, okay? But if you go through the DNA to the harmonic spectrum of each one, they are totally different. So this is the harmonic spectrum of each modulation technique. You can see in the OPP, you have lower harmonics, when in SAG you have no lower harmonics, higher harmonics. So why these harmonics are important? Because you can reduce, for example, the size of the filter installed at the output of the drive. In applications like long cables, my previous colleagues talked about subsea systems. In subsea systems, we can put a drive at the top side of the platform of, under the sea, but the cable distance, the cable length between the drive and the motor could need some kind of output filter. So depending on this application, we need to install or use special modulation like SAG. If you can reduce the low order harmonics, you can reduce the magnetics, the filter. So the power stage with simulation results, and here we can see the filter was tuned. So just for comparison, you remember the square waveform. After the filter, you have a sinusoidal waveform, which is exactly what the motor is expecting. So normally after simulation, we go through experimental stage. With the parameters, we build prototypes, and then we run a prototype to check if the simulation agrees with the real world. Using, again, those are measurements and real measurements of harmonics that fits almost with the simulation and the real results. So calculation using mathematical algorithms, then simulation, and then practical experimentation. Applications may vary on site depending on the requirements. So sometimes modulation like OPP is required or is the most benefic, like if the system, the installation, the motor is new and supports the waveform with a high content of TAG, or sometimes the motor is existing, is not able to handle such square waves, so we have to install the filter, for example. So in this work, we just collect and summarize some numbers to show the results of OPP, SAG, and SAG with filter. You can see the figure of the number that we use to evaluate is the total harmonic distortion of the voltage. So simulated versus experimental, the values are very close. And then, of course, if you have SAG with filter, the harmonics content is much lower, like a sinusoidal waveform. So those are some examples of converters that we have. For example, this is a 3 megawatts converter, and 8 megawatts converter with output filter. I can stay longer because I'm the last one, but the chairman will decide. I think the proper word is shukran.
Understand a little bit better the benefits of the filters that you introduce into your projects in terms of we in desalination strive for energy reduction and for minimization and pushing the envelopes down. My first question, since I'm the one that is moderating, I can ask you the first question, which is, what is the benefit that you see from the filters that you provide in terms of energy efficiency of the system?
That's an excellent question, thank you. We are always looking for the converter side, we are always looking to reduce the losses, always. This is a market pressure. So sometimes for the application we have to use a filter because the application requires, right? The benefit to use some specific innovative modulation is to try to reduce the size of the filter, so the losses of the filter itself will reduce as well, instead of a regular modulation with a big filter. This is one of these benefits. Use the mathematical and the computational strongest to reduce the magnetics.
Thank you. Well, any questions from the audience? Yeah, it is an interesting topic. If there are no more questions, you could think about it. The topic is very specific for us, many of us being chemical engineers. But yes, please.
Hi, I'm Casey Bly from Fluid Equipment Development. I'm the VP of Sales and Global Operations. So again, you're looking at a VFD that has connected to a 3 to 8 megawatt motor. The efficiency of that drive will probably be 97 to 98%. Is that correct?
That's correct. The efficiency of the power electronics itself without filters is roughly 99%. When you add filters, it can reduce 0.5. So power electronics plus filter, 89.5% roughly. But you have to consider the efficiency of the system. You have to consider the efficiency of the transformer and the efficiency of the motor as well. Okay. But the power electronics, we can reach 99% is a real number.
Okay, excellent. Have you guys looked at the idea of using a single drive to start multiple motors and switch over direct online? So you have a bank of, like, say, 10 high-pressure pumps. And
can you repeat, please?
Yep. So you have a bank of, say, 5 high-pressure pumps, and you're using the VFD to ramp up the high-pressure pump, switch over direct online, so you're not losing any efficiency. And then that VFD would be neutral, and then you'd actually go to the next high-pressure pump and ramp that one up. So you're actually using the VFD as like a soft starter. And then throughout the system, you would have a single point that would have a variable pressure to control pressure in the system.
That's a good question. We do use soft starters, but soft starters limited to because of the size of semiconductors that are available on the market. For certain power range, we can recommend soft starters to ramp the motor and connect to the line. But for high power, like higher than 6 megawatts, normally we do recommend the VFD to do this same work to ramp up and then connect to the line, if the application does not require a speed variation.
Thank you. Any other questions? I'd like to ask one more question while you're thinking. It's, do we have a benefit from what you offer, the techniques you offered, in terms of dealing with power surges that sometimes occur in our power supply systems?
You mean power surges from the mains?
Yes.
Yeah, normally the system has input circuit breaker, transformer, and the drive itself and the motor. And the input circuit breaker and transformer, we do recommend to use surge arresters and snubber capacitors for this transient of the mains.
Okay, thank you. Any other questions from the audience? Yes, everybody's tired. It was a long day.
Sorry for that.
Any questions? Okay, if there are no more questions, I would like to thank you again in participating in this session. It was an interesting session, very specific topics to what we don't see as much often in our field, but I think it gives you a lot of food for thought. And again, I think what was presented in the first session, you're welcome to break tomorrow, which breaks the subsea system, which is at the check-in area. So with that, I would like to close the session for today.
Thank you.
And thank you again. Thank you very much.
Well, thank you to our excellent speakers and session chairs for a really exciting session, something that always really interests me personally. Now that we've wrapped up the session, please feel free to depart the stage as you feel comfortable, and we'll wrap up the day. So thank you to all of the speakers that we've had today. What a day we've had. We've navigated the local and global best practice and approaches to innovation in desalination. We've heard about how to maximize the economic and environmental outcomes from desal. We've learned about how we can better utilize the tool of digital to help desal become even more efficient in its delivery of essential water services to communities, agriculture, and industry. I hope you've all enjoyed the first day as much as I have. Please join us again tomorrow morning at 9 a.m. for another energized and insightful day. For now, good evening and good night.